Okay, thank you. Thank you for the introduction. It's great to be back. This is the one place I come every year. I have met future PhD students and future postdocs in this room. I don't always remember until later, but I'm delighted to be back and to tell you about sequence models. So this is, last night's talk by Kyung-Hyun was fantastic, very cutting edge, talking about things that are going on right now, some issues that are very near and dear to my heart, and really got me in the mood. But today it's gonna be fundamentals. We're gonna learn very basic things that I think everyone who works in the field of AI should understand now, that language models are the center of everything. And so I'm going to start off. This is going to be a technical lecture. It's going to lay mathematical foundations to help you understand language models, whether they're large or small or whatever. But I also have something that I like to plug in these settings because you might know somebody who doesn't want the mathematical details. I don't know, your mom, your friends, your kids. So we wrote a tutorial called Language Models, A Guide for the Perplexed a couple years ago. It came out on the first anniversary of ChatGPT's release. And so that's out. It's on the archive. There's a talk video on my website. If you know somebody or a group of people who need like a more gentle introduction that's less mathy, I recommend it because I think more people in the broader public need to understand language models and need to have some critical thinking skills. So some of the issues that came up in Kyung-Hyun's talk last night also come up in that tutorial. Okay, but we're going to do the math today. I don't think I need to motivate language models for you. Some of the things in these slides I've had in here a long time, but just to kind of get your brain going in the right place and warm you up. You're in the middle of writing an email or a text message or I don't know, a scientific paper, and you start writing, and then you have the system predict the next word. This autocomplete function, which we all use all the time, whether we want to or not, is the heart of the language modeling task. What is the next word likely to be given what's already been written? And I think we all have seen this in action with chat-based systems like ChatGPT and Gemini and many others. You ask a question, the system responds with an answer. So what it's kind of doing is predicting the next word as if it was a dialogue between people, right? In fact, it feels so much like a dialogue between people that I think we often forget that we're talking to a system. We think we're having a chat. In fact, that system is predicting the next word. That is all it is doing, one at a time, the next word, the next word. There are many other motivations from the history of AI and natural language processing and speech processing that have language in some form as output. And these were some of the original motivations for building language models. So language models are a lot older than ChatGPT. You can find them in the literature going back, I think, to the 60s, definitely to the 70s. But they emerged really in the field of transcribing speech to text, something that we all have systems that do this now with pretty high quality. If you speak a language with high resources, this is now a very commercialized product, and that was really, it didn't always work, right? The older people in the room can tell you there was a time when it was pretty crappy. It wasn't really worth paying for, and part of the way that speech recognition got good was through the use of language models. The same thing for automatic translation between languages. A key part, we'll talk about this later today, of older systems for translation. Even before neural nets were in translation, we were using language models to help make translation better, and many more. And so the way I would talk about it in kind of this older setup, where language models were really born, was you're mapping some kind of input. It could be an image, it could be an audio signal, it could be anything, it could be a long document. You're trying to map that input, whatever it is, into a word sequence, which is a summary or a transcription. And there are two parts to what you want out of that output. You want a word sequence that's faithful to the input, so we can denote that with turn it on. Oh, we just did this. We tested it out before. Did I leave it on? Yeah. So you want a score of faithfulness. You want the words that come out to be faithful to the input, but you also want them to just on their own be fluent in the language that you're trying to have the system output text in. And so language models were the fluency score. So you had something else that said how good is this word sequence relative to the inputs that you got, And then you had something that the language model would give you this score that says, yeah, these are good words. This is good English, or this is good Portuguese. And I will put forward that we don't hear a lot about science, notwithstanding Cho's remarks last night. These days, there's so much engineering, but there are people who are interested in building theories about language. And if you have two theories, A and B, a classic way to think about the quality of those theories is how surprised are they by the data? How well do they fit the data? And you want to prefer the theory that explains your data better or is less surprised by your data. So language models, as we'll see in a few minutes, can give us a notion of surprise. So I don't think this is very widespread. I think this accounts for a small fraction of the work being done in AI today. But I think it's a perfectly valid view that a language model can be understood as a very far-ranging theory of a language. All right, let's start by talking about probability. So in this lecture, all the event spaces are going to be discrete. I don't know if that was the case in Mario's lecture. No. So if you're a computer scientist at heart, you can relax. And if you're an engineer at heart, then sorry, this is going to be less fun for you. This is like the divide. Are you a discrete person or a continuous person? Mario, I think, is a continuum. Well, Mario is both. So our event spaces are going to be discrete. I'll use script notation for event spaces. We have random variables over them. We use capital letters for that. And so we have statements like random variable capital letter X takes value little x in script X, which is the set of possible events, with probability P big X equals little x, or if we're being quick and dirty, we'll just say P of little x. So whenever we give probabilities, there's some random variable at play. And we always, language is complicated, so we always have more than one random variable, almost always. So we'll talk about things like joint probability. So this is the probability that random variable big X takes the value little x, and probability and also random variable big Y takes the value little y. And of course, we have conditional probabilities, and we know that the definition of conditional probability is that you can think of this it is mathematically defined. You can't just think about it this way. This is what it is. It's the ratio of the joint probability of the two events to the marginal probability of the right-hand side event y. This is going to be very important, this conditional probability. And so given that definition, there are some things that are just always true. The joint probability can be decomposed into a conditional and a marginal, and you can do that in any direction. You can either take the marginal of y and then multiply in the conditional of x given y, or the other way around. Both are correct, both are always true. And then there's this thing that's sometimes true. Sometimes it's the case that the joint probability is the product of the marginals. When is this true? What is the... I heard two people say the word independent, and that is correct, right? So you have independent random variables means that the conditional is it just collapses and it's equal to the marginal. The other thing I like to point out as we dive into probability, there's often a sort of conflation of the idea, is there a true probability distribution over the next word? That's an interesting philosophical question, and we could argue about it all day long. What we're mostly dealing in when we're building practical AI systems is estimated probability distributions. We're making the assumption that this is a distribution, that it exists, and that we get evidence for it through data that has been sampled through some natural process, and we're estimating the probability distribution. So almost always when we talk about probabilities today, we'll be talking about estimates of some probably fictional true distribution, and we'll be making some assumptions that are probably not 100% correct for convenience. Okay, so now let's get into some notation specific to dealing with natural language. The first big one is we need to decide what set of symbols we're going to model in our sequences. And so we use script V to be a finite set of symbols. These are usually it's helpful, I think, in the beginning to think of them as words, or maybe characters, or maybe bytes. You can find all of these in the literature. Most commonly today, the set of symbols that we are modeling are something less than words. Maybe words, sometimes smaller pieces of them. We'll talk a little bit more about that later. But abstractly, we're going to call it script V. It's large. I think today it's not uncommon for the vocabulary size to be somewhere between 100 and 200,000. Sometimes bigger, sometimes smaller, depending on the application. And so borrowing some notation from theory of computation, we're going to let V star be the set of sequences over symbols in V. So there's infinitely many things in V star. This is all the sequences that could ever be imagined. This includes all sequences in English, all sequences in Portuguese, if our vocabulary is capable of handling it, Python, etc. Okay. So what we're going to do in language modeling is we're going to imagine a sequence of random variables, x1, the first word, x2, the second word, and so on. And it just continues until some x at some point takes a special value, which I denote as a stop sign. So this is like a stop symbol that says, all right, you're done, don't generate anymore. And so if we want to be really, really fastidious, then we'll use VDagger to be the infinite set of sequences of V symbols that end in a single stop symbol at the end and have no other stop symbols anywhere else. And that's really the event space for a language model, is this VDagger. Any questions? All right. All right, so here's the language modeling problem in its simplest form. You're going to get a training data sequence. Call it bold little x, so bold just means sequence, or you could write it as little x1 up through little xn in VDagger, which means little xn is the stop symbol. And I'll just sort of hedge here. Sometimes it's more useful to think of this as a collection of observations rather than just one, but that will complicate the notation. So for now, we'll just think of it as one sequence. It's very long. It could have trillions of words in it. And what we're going to do is estimate a function p that can map any sequence in VDagger to real values that we're going to think about as measure of plausibility. Okay. So what we're trying to do is generalize from the training data to any new sequence of language that we might encounter in the future. So that's it. We're done. That's language modeling. Thank you very much. So, okay, so what we're going to talk about with the rest of the time today is mostly how we build them. But before we talk about how we build them, we're going to talk about how we evaluate them. And we'll talk a little bit about how we use them and how they've been used through history. I'll give the warning now, since we're still at the beginning. I'm basically going to carry you up through many generations of language models, but not the transformer. We'll do everything we need to set you up to understand the transformer when you learn it tomorrow, I think. Yes. So this is all like pre-transformer, and then when you come in tomorrow, you'll be totally set and you'll be able to focus on the weird stuff that happens in the transformer, and you won't be confused about language models. That's my hope. So let's start with evaluation. I want to say a little bit more about this scoring function that the language model defines. So P is going to be a probability distribution. So really, when we say language model, what we ought to say is probabilistic language model or generative language model. We're defining a well-formed probability distribution over all the strings in VDagger. And that means that we're assigning a value at least 0 to every one of them. And if you sum up the scores of P of x across all the x, all the infinitely many x, you'll get a value of 1. People love probability. Mathematicians love probability. Probability gives us two main things that continue to be appealing in language modeling. One, it gives us a kind of interpretability. And it doesn't give us maybe all the interpretability that we want, but we understand probability. We understand how to compare two values in a probability distribution. Probability gives us at least some sense of what the model might do next when we consider a next word prediction. It also, using probability and setting this up as a probability model rather than some other arbitrary scoring function, also allows us to use a fantastic tool from statistics called the maximum likelihood principle, which I think you heard about yesterday. Yes? Nobody remembers it except Mario, but you learned about maximum likelihood yesterday. We're going to apply the maximum likelihood principle to build language models from data, and that's even true today. And so that gives us, I don't know, some mental hygiene. It's like we don't have to reinvent our estimation procedures. We can reuse time-tested tools from statistics that have been around for a long time and have some confidence that what we're doing is reasonable. So here's, let's quickly review. If you have data, let X be your observations, and you're considering a set of probability distributions that are consistent with our assumptions about the data. So let that set be script P. Then you should choose the distribution from that family P that makes the data as likely as possible. That's the maximum likelihood principle. And in practice, that script P, it's very highfalutin and abstract. What we actually do is we say, this is a family of probabilistic models with some parameters theta, and we're going to choose the values of theta that will maximize likelihood. So what we're really choosing are the parameters. We've already sat down and thought hard about what we want our probability distribution to look like, what assumptions we're willing to make, and we've chosen a family, and now it's just a matter of turning all those knobs and doing the optimization procedure. So classic MLE example, you've got coin flips. I'm going to give you the discrete one because usually people give you the Gaussian, and I think it's good to see the discrete version. So this is the simplest kind of discrete probability distribution. You've got a coin that you're going to flip n times. It either comes up heads or it comes up tails. That's your event space. And so if we make some assumptions, so this is now choosing our probability distribution family, we're going to assume that it's a single coin that gets flipped repeatedly, and the observations are independent and identically distributed. The coin doesn't remember what happened on the last flip when you flip it the next time. That's a very important assumption. And so basically there's one parameter, which is the probability the coin comes up heads. We'll call it theta. And we want to estimate theta. If we write down the probability of the data, it looks something like this. We have a product across our n flips, so from 1 to n. And we basically either multiply in a theta if it came up heads. So if xi was heads, then we multiply in a theta. Otherwise, this goes to 1 because that little indicator function is 0. And if it didn't come up heads, if it came up tails, we multiply in 1 minus theta for every tails. And if it didn't come up tails, this exponent will be a 0, and so that'll multiply in a 1. So basically, every coin flip, we either multiply in theta or 1 minus theta. So that's the likelihood. That's the probability of the data under a particular theta setting. And then our optimization problem is to choose the theta value that maximizes that function. And I'm not going to go through the derivation. It's pretty simple. It needs a Lagrange multiplier. But basically, you can easily prove that as long as you have at least one flip, the maximum likelihood estimate will be the intuitive thing. Count the number of times you got heads and divide it by the total number of flips. Count and normalize. That's all you have to do to get the maximum likelihood estimate for this very, very simple model of IID coin flips with a single coin. More generally, if we have multiple different kinds of events, like imagine it wasn't a coin, imagine it had more sides, it was like a die, like in gambling. If you go to Vegas at a casino, they roll dice all the time, or some other distribution over many possible events. If you make a similar assumption that it's like a many-faced die and it's memoryless, then maximum likelihood estimation continues to have this simple form. Just count the number of times each event happened, normalize the counts, and those give you the probabilities of the different events. Okay, so enough background about probability. Let's talk about how we actually evaluate language models. We're going to make use of this probabilistic definition of language models in evaluating them. So one of the things that comes with talking about probability is that we can develop a notion of surprise. So again, remember I said way back, one of the motivations for building language models is we can think of them as theories of the data. And if we want to compare two language models as theories of our data, then we should ask, which language model is the least surprised by the new data? Very important that we use new data that wasn't used to build the language model. Why? Why do we have separate test sets? Why was Kyung-hyun so obsessed with this last night, and why am I saying it again now? And Mario probably said it too. Got to have test data. Why? Fresh test data. We want the model to generalize. The analogy I like to use is imagine this was not a summer course, but a university course. And at the end of the week, you were going to get an exam. And imagine that the absent-minded professor, definitely not me, definitely not Mario, but some other absent-minded professor, accidentally left the answer key to the exam lying around on one of the tables at the coffee break. And one of your colleagues saw the answers. Would we trust their performance on the exam if they had seen the answers to the questions before the exam happened? I don't want to cast any moral aspersions. I don't want to say they're a bad person. I don't want to say they cheated, but we cannot trust their performance on that exam if they already saw the answers. That is why we must keep test data separate. We call it the test data because it's a test. If the language model got to see at any stage during its development the test, then the results are invalidated. And we could use the word cheating. I like to just say it's not a valid test. So what we usually want is data that's drawn from distributions of interest that are relevant to the real applications where we want to deploy the language model. That might be similar to the training data. It might be very different from the training data, but regardless, we want the test data. We need the test data to be something that was not in the training data. A word people sometimes use these days is contamination. We want to make sure that the training data is not contaminated with anything that's going to show up in the test. Very important. Okay, so lecture about test data over. Just remember this for the rest of your lives. If you commit no other sins, never train on the test data. Never use the test data to pick your hyperparameters. Keep it separate. Okay, so let's assume we have a fresh, clean test data set. We'll call it X bar. And the standard intrinsic evaluation of a language model, we get there in 3 steps. This is going to look a little weird, so don't panic. First, calculate the probability of the test data. Okay, no big deal. This is just a measure of how surprised the language model is to see this new data. But it's not exactly a measure of surprise. It's actually just a tiny, tiny little number. Okay, this is going to be, remember, the probability of all possible sequences has to sum up to 1, which means it's like we've got one big pie and we're carving it up among infinitely many different sequences that could ever be produced. So the number you're going to get for this one test data sequence is going to be astronomically small. It's going to be so small that your brain won't know what to do with it. It'll be like 10 to the negative something, right? Tiny, tiny, tiny little number. So it's not very interpretable. It's not very meaningful. So the next couple of steps are going to be a way to transform it that give us something that's more interpretable, that's more standardized. The number is tiny because the event space is huge. And P is going to decrease exponentially in the length of X bar. So we transform it in a way that makes it, that sort of normalizes for the length of the sequence. So here's what we do. We take the inverse. So we take 1 over that probability, and then we take the n-barth root. Okay, so this is, the way you can think about this is it's like, first we're going to take a tiny little number and we're going to make it big, because taking the inverse of something that's less than 1 is going to make it much, much bigger than 1. And then taking the nth root, it's like taking a geometric average. It's like saying, on average, what gets multiplied in to this inverse probability for each word? So perplexity is a number that, sorry, I'll show it another way because sometimes people really flip out when they see that n root. Another way to write it is you take the log probability, okay, divide it by n bar, and then raise 2 to that power, exponentiate. These are equivalent. You can show that they're the same. They'll give you the same answer. The log probability thing is sometimes a little easier for people to get because it's the log loss. It's what you actually, if you're familiar with how we train language models, and if you're not, don't worry, you'll see it again later. That is kind of what we're minimizing on the training data, the negative log probability. And what we're doing here is we're again normalizing it for the number of words that are in that test set. So, okay, so if your mind is still spinning and this doesn't totally make sense, let me talk through a couple special cases that will hopefully make it more clear. First, I want you to imagine the most wonderful, amazing language model that was ever built. This language model is so intelligent, it can predict the future. And it knows exactly what test set you're going to. It's so smart, it predicts the test set before you even give it the test set. And it puts probability 1 on your test set. And it didn't cheat. It's just so good, okay? This is a fiction. This doesn't exist. We can't imagine how this could possibly come to be. But if it did, then that P of X bar under theta would be 1. And if you go through the steps, if you take 1 over 1, you get 1. And if you take the n bar root of 1, you get 1. Perplexity would be 1. This is the best perplexity that could ever be achieved under of all possible models. That's not going to happen. But the closer you get to 1, the better your language model is on this test set, the less surprised it is. Another edge case that's worth talking about, imagine the model put 0 probability on X bar. You messed up, okay? You messed up bad. Your model didn't generalize well, and it said 0. It's like, this can't happen. What will happen is you get 1 over 0, which tends to infinity. It doesn't matter if you take the root. Perplexity goes off to positive infinity. It's infinitely perplexed. This is bad. So basically, because of this this is kind of an interesting historical note. Because of this particular way of evaluating language models, it's historically always been very important that when you build a language model, you make sure that it never gives 0 probability to any sequence. It's always got it. So this is like a slight modification to what I said before. It's always got to be slightly positive. You've always got to save a little bit of probability mass for anything at all, because you never know what will happen at test time. And this played a really big role in language modeling literature for I don't know, about 20 years, until neural models came to the fore. Many papers were written about how you make sure that the probability mass is always strictly positive on any sequence. Final note, if you really want a way to interpret perplexity, if you get into the information theoretic analysis of what's going on here, then you can think about the perplexity as kind of like a branching factor. It's like, on average, at every step, as the model is predicting what word will come next, how many words in the vocabulary is it choosing among? If the perplexity is 1, that means the language model is always just choosing 1 word. It knows what's next. It doesn't really have to make a choice. It's always betting on the right thing. If it's very large, like say the size of the vocabulary, then that means the model is choosing among many, among everything. It really has it's not using the context information to predict what comes next very well. Okay, some warnings. Perplexity is not the end game. Perplexity is a very useful tool when you are building a language model or when you're doing controlled, careful experiments to test ideas about language modeling. But there are some shortcomings. First, you can really only compare perplexity of models that use the same vocabulary. There are some things people do to correct if they're using different vocabularies. There's a measure called bits per byte, which is frequently used, and it's okay. I'm not going to tell you not to use it, but strictly speaking, from a mathematical perspective, it's a little dodgy. Traditionally, you would only think about comparing perplexity of 2 models that had exactly the same vocabulary so they're putting mass across exactly the same event space. People often take accepted test sets when they write language modeling papers, and they report perplexity on those test sets. I'm not going to talk about absolute numbers. They get lower every year. These days, we see perplexity less than 10. Which was if you look at some of the textbooks from when I was learning this stuff, they would say things like, really good language models are getting perplexity below 200. Now it's much smaller. The models are getting really good from this perspective. I think remembering specific perplexity numbers is kind of a fool's game. Your data is always going to be a little different than the specific test sets that people use in papers. So I think take the numbers with a grain of salt. They're useful for making comparisons in kind of a local controlled experiment setting, but don't take the perplexity of a model on a particular test set as an entire measure of its quality. In fact, we argued this recently. So we had a new benchmark. If you can believe it, there were not standardized benchmarks for Perplexity. There were just a few data sets that people kept reporting on. We built a Perplexity benchmark of more than 500 different test sets with a wide range of different properties, and started advocating for doing very rigorous analysis across many different test sets, because we think a language model that's really good at, say, scientific text may not be good at other things, and what you want may be something very specific. So yeah, so that's even a fairly recent development that we've started thinking of it as benchmark worthy. Okay, moment for reflection while I sip some water. Let's imagine we can calculate the perplexity on any data set at all. So we could go back to the training set and say, what's the perplexity on the training data? So I want you to think about that for a second. Do you expect training perplexity to be lower or higher than test perplexity, and why? Think about it for a minute. Don't rush to a conclusion. You get some think tokens. Okay, who says training perplexity will be lower? Who says it will be higher? Okay, I feel like I'm not getting independent draws. People are influencing each other. I agree with the majority that perplexity should be lower on the training data. Somebody tell me why. Just shout. Yeah. You have a large data set, but you could have a large test set. The model saw the data. In fact, you could argue that what the model was trained to do in most cases was to drive down perplexity on the training data. That is the training signal that it actually gets. If you look at that perplexity term, if you take the log, so you're just looking at this, what are you doing when you do maximum likelihood estimation? That is equivalent mathematically to reducing the perplexity or the log perplexity on the training data. So the model was optimized to get low perplexity on the training data. The test data, if you did things properly, is new, fresh, different. It's never seen it before. So you should generally expect it will be lower on the training data. Okay, yeah. Oh, sorry, question. Go ahead.
Excuse me. Thank you very much. I have a question about the perplexity. So can we use it as a advantage word function while we are training our model?
Can we use it as a reward function?
Yeah.
I wouldn't call it a reward function. I would call it an objective. I would call it the training objective. When we train our model, we're getting a little ahead of ourselves, but that's okay. When we train our model and we apply the maximum likelihood principle, what we are doing is minimizing. It is exactly the same as minimizing the perplexity on the training data.
I mean, just in case where we are using post training with reinforcement learning.
So I would put forward that there's absolutely no reason to use reinforcement learning if this is what you want to minimize, because you can calculate it and take a derivative and just do SGD and go down. Okay. Usually reinforcement learning becomes appealing when we can't take gradients.
Thank you. So it is possible that the data set contains a bunch of independent texts. And if, for example, we consider large language models, they just do this. They calculate conditional probability based on the prefixes. But if we have a bunch of independent texts, should we just consider how we should calculate this probability? Should it be like multiplying of multiple probabilities for each text?
Yes. Yeah, that's a great question. So this is I'll say it back in a slightly different way just to make sure people understand. So let's go back to, we'll just use this notation. So think this is X, not X bar. So this is the training data. And what I'm trying to do is minimize this negative log probability, or in other words, maximize the log probability of the data. The question is, what if that data isn't one long sequence? What if it's a whole collection of independent documents or books or pieces of text, tweets, whatever, emails, hopefully not emails, then what should I do? And the answer is basically, if you assume they're independent, then you should multiply together the probabilities of each of the pieces of text, or equivalently sum up their logs. And that is what we do. Well, sort of. What we really do is, we batch the data with modern language models, and we batch it in very large batches that might have a lot of different documents. You can mask away the history that consists of other documents, so you're kind of starting fresh on each sequence. You don't always do that for various reasons. But basically, that is what I would say you should do, is you should sum up the log probabilities across the independent samples. Yeah, good question. Yeah, question over here.
Why we don't use the perplexity as a loss function in our models?
So we do, but we transform it to avoid numerical issues. So if you think of, again, we're talking about the training data here, not the test data. If you take the log of this function, right? So you're canceling out this 2. Then what you're doing is you're taking a monotonic function, right? And so instead of minimizing this thing, you minimize its log. It's going to give you the same. The minimum will be the same because log is monotonic. And it's much, much nicer to deal with negative log probabilities than it is to deal with these exponentiated values.
So it's like cross entropy loss.
It's cross entropy loss, exactly. Yep.
Okay. Thank you.
Yep. Okay, let's keep going. So this I think is one of the underappreciated problems in language modeling, because we all want to think about these cool math problems and parameters and scale and lots of data and all that fun stuff. But one of the things that you have to do before you start building your language model is choose the vocabulary. And this is one of the little corners of AI where knowing a little bit of information about natural language can be very useful. So here's the very naive solution. If you are an English speaker or a Portuguese speaker or a speaker of most Western European languages, basically use white space. White space is a gift that tells you where meaningful units of text break. And when we read text with our eyes, we naturally break it into words. And we just say anything that's between white space becomes a vocabulary element. And that's our vocabulary. We just look at the training data and say everything that I see between white space is going to be a word, and that's how we break the text up. The reason that one reason we don't do this is that this will be a very, very large vocabulary. In the old days, when NLP was largely done on very clean, carefully edited text, like news text, this wasn't such a big deal. But today, we train on the internet. And the internet contains every possible misspelling of every word you could ever imagine, every variant of capitalization, adding punctuation on in every possible way. There's just a huge, huge number of possible things that could be in your vocabulary if you only use white space to separate things. Also, think about emoji, right? Think about the many, many things people cook up when they're putting symbols together creatively. There's just going to be too many things in your vocabulary. There's another problem here. If you get outside the Western European languages, some languages, like notably Chinese, do not use white space. There's just nothing there. So how do you break that into pieces? What are you going to do? So this white space solution, it's not what we do. There's another simple solution that's very, very, very safe that is appealing. And in fact, this idea never goes away. People keep trying to figure out how they can make it work because it's really beautiful. Just forget everything about language. Forget that you're dealing with language, and say what I'm really looking at is a sequence of bytes. Everything is a byte, and when we encode text in Unicode, it's variable numbers of bytes per character, but never mind. We just take byte, 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 and we predict sequences of bytes, and we can reassemble those and interpret them as Unicode or UTF-8 or whatever. So this is great. What will be our vocabulary size if we allow all the bytes and nothing else? How many bytes are there? 256. Beautiful, tiny little vocabulary size. What's wrong with this? The problem is, this doesn't generally work in practice because it's basically breaking up all the structure of language into these little tiny pieces, right? It's literally byte by byte by byte. And so the length of a word, the length of a semantically meaningful unit will be much longer than if we could treat a word as a single thing or a small number of things. So basically what happens is the sequence length gets extremely long. You're trading vocabulary size for sequence length. And that might not seem like such a big deal because the sequence lengths are getting longer and longer and longer, but people really are using those sequence lengths today with things like chain of thought and packing in lots and lots of context or retrieval augmentation. You really want as much context length as you can, and you want to be able to pack as much information as you can into it. The multiplier on making every character multiple, 1 or more bytes, sometimes up to 4, it's just huge. So this is just not practice. There are some research systems that are trying to do things with bytes, and some of them are pretty interesting. But in wide deployment, in conventional state-of-the-art systems, we're not doing this, at least not yet. Here's what we actually do. Okay, I like to give the extremes that we don't do and then give you the thing that we actually do. We actually have a data-driven solution. We take a sample of data, might be part of the training data, and we learn a series of rules. We start by saying every byte is in the vocabulary. So our vocabulary starts out at 256. And then we iteratively look for sequences of elements of the vocabulary, so at the beginning, bytes, that are extremely frequent. And so we take our most frequent bigram, our most frequent pair, and we merge it and say, this is now going to be in the vocabulary. And everywhere we see it, we transform it to be that new vocabulary element. And we just repeat this greedy merging until we get the vocabulary size we like. This is called byte pair encoding. There are a few other variants of it. The byte pair encoding one is the easiest one to teach without even showing the algorithm on the screen. And it's the basis of most vocabulary building systems today. It matters a lot what data you choose for running your byte pair encoding algorithm. But it's a pretty good approach. There's some details that I'm not talking about. Usually what happens is you do something called pre-tokenization before you do byte pair encoding. And you forbid merges across white space, for example, so that you learn subword units rather than crossword units. Some new work from my group coming out at Colm starts to look at, we call it super BPE. You at some point relax that constraint and start allowing merges across tokens so you can get bigger multi-word vocabulary elements. It turns out that's really great for efficiency and performance. But I'm getting ahead of myself. The most common starting point is byte pair encoding. And it's a very simple algorithm. You can find implementations of it on Hugging Face. And this is how most language models start out. So what you get are subword units, sometimes full words, sometimes pieces of words that are easy to assemble. And it's a deterministic transformation of the data. So you don't spend a whole lot of time putting these back together after your language model generates. Yes, question. I can repeat it. Go ahead.
So like you were saying, well, we could just like use bytes, but then like if we just use bytes, we would have like to have like a lot of tokens, and that like increases complexity because like your sequence length.
Maybe the model can learn through that, but
big.
so far it's not a competitive solution.
Yeah, so what you're saying is like we want like smaller like units, right? Like so we have less of them, so we can like process more efficiently.
You want bigger units so that your words are broken up.
No. I mean like you want like smaller like sequence lengths,
You want smaller sequence lengths.
Tokens that
yeah.
find more characters. So like, but if you do that, like at the same time, like so like there's like a trade-off here. Because like you're gonna have like to output like a lot more probabilities in your probability distribution because you have like more.
You're going to have a bigger vocabulary.
So what?
And it's going to be sparser. Yeah.
Like what I'm trying to say is like, where do you draw the line? Because like you could just like assign like like a new token for every possible word in the universe. You could say, well, then you have like a or you could even say one token is every single text I saw, like it's the most extreme thing, right? Like but I mean if you do that, like it also becomes like super complex. So where's the
the way I like to think about this and many other things is there's a trade-off between the quality of what you build and the efficiency of building it and operating it. So basically what you're pointing to is an efficiency trade-off. you could maybe get a very, very, very efficient model, but it's going to come at some cost somewhere else. Or maybe there are different notions of efficiency. Like maybe if you have a huge, huge vocabulary, you're going to need a whole lot of parameters to represent everything that's associated with all of those words. And at some point, that is going to trump the cost of having, this very rich vocabulary. So what's the right point? Well, what people do is they try things, right? So there's lots of existing solutions in the literature where people chose, this was my vocabulary size, this was how I built it, this was my model size, this is how well it worked. And we measure how well did it work, both perplexity and extrinsic evaluation on benchmarks of interest to the community, right? We decide what makes a good language model, and we say, what was the cost of building this, or what is the cost of running it at runtime, and how well do we do? And then we compare that to something else. And what you get is a curve that says you're trading one thing against another, and in a practical setting, you try and pick a point on that curve that makes sense for you. There is no universal solution to this. There are probably going to be situations where a byte-based language model actually is a great solution because the footprint is so much smaller. And having that longer sequence length might be perfectly okay because you're only doing very, very short chats. I don't know, right? So I tend to think there's a wide universe of possibilities, and there is not going to be one size fits all solution for everything. You have a question? Yes.
Like, what are the thumb rules to separate test data set and train data set? Since we are doing with sequence of token, like if we have part of sequence is repetitive between training and test set, do we have astral measurement to do this?
Yeah. So this is a great question. I mean, most of the time, people sort of separate the research on setting up the test set from building the models. But often, if you're building your own solution, you're going to have to think about this. What's going to be my test set? And it's sort of up to you how much energy you put into this. On our team, so I didn't talk about this yet, but it was going to come up sooner or later. I work on a team that's building Olmo, fully open language model. We're building Olmo 3 right now. Our team is obsessive about this. When we know what we're evaluating on, we do extensive decontamination of the training data. We look for anything that's a close match to anything that we're going to evaluate on later, including downstream evaluations, and we scrub it out of the training data because we want very, very scientifically reliable measurements of how well the model does on these things. We don't know if other teams do this. We don't know. I hope they do. We suspect they probably don't. But we could probably invest more. Deduplicating text, finding anything that looks like this one piece of test data in my training set is actually a very hard problem. Like how similar can it be? It's a tricky question. You could do exact match, but maybe you should look for things that are only different by a little bit. And there's a wide range of tools for doing this kind of filtering. Deduplication is the key word. But it's sort of up to you. I think if you're trying to write a scientific paper, you should be aggressive about decontaminating your training data. Great question. Okay, I wanted to say one more thing about this byte pair encoding solution. It's very appealing from the following perspective. It doesn't, if all the bytes are in your vocabulary, then suppose somebody gives you some new text that's really different from anything you saw. It's got a whole bunch of new words. It's in a language that you never trained on. You're actually going to be completely safe because in the worst case, if your tokenizer can't do anything, it can't form any meaningful units, any larger tokens out of that input text, it can always fall back to bytes, and there will always be a probability distribution that goes byte by byte. So you sort of protected yourself, especially if your training data is a little bit noisy and has some random stuff in it, you will always have a probability of every byte coming next. So you'll never have the zero problem. This is like for people who lived through the years of smoothing papers, trying to figure out how to make sure the probability distribution never went to zero. This is really nice. I don't have to think about it because my tokenizer protects me. Okay, we've talked about the vocabulary. We've talked about tokenization. There's a question way in the back. I'll keep talking until the poor person with the microphone gets there. So we're now not going to talk about the vocabulary anymore. We're going to assume that it's fixed and finite. Training is going to start from the maximum likelihood principle, which means essentially minimize cross entropy or log perplexity on the training data. We have training data X. We are going to evaluate perplexity on the test data X bar. Question?
Basically, I saw like in practice that working with bytes works really well, like building Markov models and trying to. I even built like a project in college that we kind of were detecting the AI generated text, and doing the tokenization by the bytes really worked really well, and it was very efficient. But my question is, how do we deal with the text that doesn't have a lot of repetitions? Because all these models like require text that you can find patterns, and there has to be like repetitions. And how do you deal with that not having a lot of repetitions? And basically, that's my question.
How do you deal with text that does have a lot of repetitions or that doesn't?
That doesn't have a lot of repetitions, so not a lot of patterns.
I mean, does natural language have a lot of repetition? I don't know. Relative to what?
I don't know, maybe not a lot of patterns, basically.
Not a lot of.
Yeah, I'm sorry, maybe I'm not explaining.
I mean,
correctly.
so this is, I think there's a deeper philosophical question here, which is like, how much repetition is there in natural language? And so, you know, there's a view that like, we're so creative and the internet has so much rich text and people say so many different things. But if you've ever looked at query logs for search engines, you know that people are not actually that creative. They all ask the same questions. So the way that, you know, the way to walk between these two perspectives is to think of the distribution over what people say as being very, very long-tailed, right? So there's a short, fat head of the distribution where we all say the same things. Good morning, hello. Today I'd like to talk about language models. All this stuff is very repetitive for me because I've given this lecture 15 times in this room. Maybe not for you yet, but then there's like a long tail of random stuff that happens and people say things that have never been said before every day because there's a lot of people and there's a lot of text. So somehow these things are both happening. There's the highly predictable part, and then there's this long tail of crazy stuff that's surprising. And I don't know, you could maybe argue that we're now pretty good at getting out into that longer tail, much better than we were in the past. And that's why language models are more useful now. I don't know. But I don't have a simple answer to that question, sorry.
No, but that's a good answer.
Okay,
Thank you.
glad you're happy. Okay, there's one, sorry, all the way down in the front, but I'll keep talking while, oh, no, go ahead, yeah.
Yeah, it's very short. So here, like you were talking about like a fixed finite vocabulary, but like, I mean, it has to be that, right? Like, I mean, there's no possible infinite vocabulary, like it wouldn't make sense.
I mean, language is always changing.
But I mean,
Every
like-
day we get new words. People invent new words all the time. That's why we have to go to subword units, right?
But how would you, like, I mean, it's impossible to model like a finite, like an infinite vocabulary.
Talk to me after the break. I can
Yeah.
point you to some papers where that's not the case.
Okay.
Yeah.
Okay. Oh, interesting.
We don't use that stuff anymore, but there's definitely something people thought about. Yeah. Okay, so here's the first language model, and I think somebody down here already sort of suggested this, but let's consider it explicitly. I proposed the maximum likelihood principle. I said for discrete things, maximum likelihood often means just count the number of times you saw a thing, and that is proportional to its probability. So you would divide by the total number of things you saw. So here's a language model. You could say the probability of the sequence is the number of times we saw the sequence. And divide by whatever you need to divide by, the number of sequences that you saw. There you go, done. Why is this not a satisfying language model? Well, what if X bar, the test data, wasn't in the training data, as it should never have been, right? So the count will be 0 and you will fail. Your perplexity will be infinite, and this is a terrible model. We would never use this model. Most people would laugh at me for even teaching this model. But again, I like to point to things that are a bit extreme to make sure that you understand the consequences of our choices. The issue will remain, by the way, even if the training data is multiple sequences, right? So if we broke up every document, every book, every piece of text separately and counted up each one, what you would mostly see is anything we had copies of would have a count greater than 1. Most things would have a count of 1, but the vast majority of things in the universe would have a count of 0. Infinitely many things would have a count of 0. So we don't do that. By the way, I call this the creepy language model. If you were to sample from this model, it would only ever be able to give you back examples from your training data. It would never be able to generate anything else. It does not generalize at all. It's creepy. So we want models that are not creepy. And the trick, the key idea that we've been using for since before I was born and probably before Mario was born, is to decompose the probability of this whole sequence down into the probabilities of its elements, each conditioned on their predecessors. Sometimes people use the word autoregressive here. I like to just think of it as, I don't know, I'm not so highfalutin, I just call it left to right. So first, the model will generate word 1. Then the model will, conditioned on word 1, generate word 2. Then the model will, conditioned on words 1 and 2, generate word 3, and so on, all the way up until it generates a stop symbol. This is my assumption that the whole thing will can be written as a chain of probabilities. And in fact, it's not even an assumption. I have given up nothing by setting up my model this way. This is just the chain rule. It's just true. It doesn't matter how I define my probability distribution. I have sacrificed nothing by choosing to think of this as a product of these next word probabilities. But when I write it this way, it invites me to think a little bit differently about the problem. Instead of slicing up that massive pie over infinitely many things, I have to design a function that gives me a new pie for every context, but the pie only has to go across the words in the vocabulary. So the game, one way of thinking about the game, is to figure out how do I summarize the information in the history, that stuff on the right side of the conditional bar, well enough to make a good prediction about each word in turn. Okay, so let's talk through some of the early language models. The most simple and elegant is called the unigram model, and it says, ignore the history. It doesn't matter. Every word is going to be drawn in the same way, regardless of what came before. So this is my assumption, is that I can just drop everything on the right side of the conditional bar. And the way we write the unigram model is as a product of the probability of each word just on its own, just happening. So if you want to think about a physical way to simulate this language model, picture if we have a 200,000 word vocabulary, picture a die with 200,000 sides. It's got every word in the vocabulary printed on some side, including the stop symbol. And all I do is I roll it. And I write down the word on top, and then I roll it again, and I write down the word on top, and I keep repeating until I see the stop symbol, and then I'm done. This model is super simple to estimate. All I have to do is count the number of times I saw each word and divide by the number of words I saw. That is the maximum likelihood estimate. As long as I saw every word at least once, then I will never have a 0 when I calculate perplexity. This model, I don't know, it's very simple. It just ignores all context. It turns out this was actually extremely useful in the area of information retrieval for some time, pre-Google. This is a very, very useful way to think about building search engines. So here's my little example. You have a sentence with, in this case, 4 words. The period at the end is counts as a word. If I tokenize on white space, just for the sake of simplicity, then in order to calculate the probability of the sequence, I have to multiply in a probability for each of the 4 words, and also a probability for stopping, because x5 is a stop symbol. In unigram notation, that's theta precedence times theta tel, and so on. And if I plugged in the maximum likelihood estimate, it's like all I have to do is store a vector the size of the vocabulary and know the count of every word in my training data. You could build this language model in probably 3 lines of Python and about 20 minutes on a very large corpus, on a CPU. You don't even need a GPU for this. Okay, so this is like you're rolling your eyes at how boring this is, but you understand the basics and it'll be easier later to get the more complicated things. Consider a unigram model that's even more simple than this. It's completely agnostic. It just assigns equal probability. It's like a fairly weighted die. It came straight from the manufacturer. Nobody has tinkered with it. All words are equal probable at every time step. What will be the perplexity of this language model? Hint, it doesn't matter. It doesn't even matter what the test set is. Can you figure it out? It will be V. Why? Yep. 1 over V will be V to the n because you had n words. And then you take the n root and the n goes away. It will be V. So this is basically like the absolute saddest language model in the world. It puts equal probability on every word, every time step, all the time. It doesn't know the history. It doesn't even differentiate among the words, and it gets perplexity V. So this is treat this as a little sanity check. If you ever build a language model and you get perplexity above V, you have a bug. You have a bad bug, right? You are not learning. The perplexity of V is as bad as it should ever be, because you should always be able to do this. Okay, unigram models. We don't use them today. None of the famous language models are making use of unigrams at present. We like them because they're easy to understand. They're super cheap. They were good enough for some version of information retrieval or search engines at one time. They have this fixed vocabulary assumption, which we don't love. We know that's slightly wrong, but we've kind of come up with tokenization methods that deal with it. That's not going to go away as an annoyance. I think the main thing people hate about unigram language models is that they're just wrong. Like, they are not this is not the way language works, right? The probability of saying the over and over and over again will be higher with a unigram model than simple sentences like "I want ice cream," because the is the most likely word in most text corpora in English. And so you can always, if you were generating from this, you would get complete trash. It would just be word salad. It wouldn't make any sense. And it would have roughly the right proportions if you sampled for a long time of most of the words. But that's about all it would have. So we don't do that. And in fact, the dominant thing for a large portion of the history of language models was a generalization called the n-gram model or Markov model. And so here we go back to our chain rule representation. Again, this assumes nothing. And we apply the assumption that what matters for predicting the next word is the previous n-1 words. So what we're doing, instead of a single die for every that's rolled repeatedly for every word, is we have a different die for every context of n-1 words. And so the unigram model is the n=1 case where there's a single die. But in general, what we had were a few periods of history where in practical systems, people were using trigram models, which means condition on 2 preceding words. And then there was a long period where it was like 5 grams, condition on 4 previous words. And so the idea here is quite simple. You have to estimate these conditional probabilities of a word given its fixed window history. So what is that? What is that maximum likelihood estimate? Again, it's going to involve counting, but things are a little bit tricky here. We're going to have a history. We have 2 random variables we have to think about. So we're in abstract notation, we're thinking about the probability of the next word given the history of n-1 words. So it's a conditional probability, which means definitionally we should think of it as a ratio of the joint probability of the full n-gram, the history followed by V, divided by the probability of the history. And we know how to estimate both of those by counting and normalizing. So what we have is really a count of the n words in the n-gram, including the next word, and then the n-1 words in the history. And the n's cancel out. And so what we get is a ratio. How many of the times we saw this history H, how many times did we see this next word V right after it? There's a common mistake where people forget that it's a conditional probability and they estimate just this numerator here, which will always be too small and will give you really crappy perplexity. So don't do that if you ever build an n-gram language model. Okay, so that's the n-gram in a nutshell. I want you to think for a second. If I give you a sequence of, imagine you have the training data, you can do whatever you want with it. Now I give you a new test sequence and I want you to give me its n-gram probability. Say we're doing an evaluation. We're competing who can build the best n-gram language model. What do you need to do computationally? What is your algorithm going to be for calculating the probability of this new test word sequence? How much time will it take and what data structure, what kind of data structure are you going to need? Matrix, that's going to be a big matrix. I'm going to say no to a matrix. You don't need dynamic programming. We're narrowing in. You're going to need to store the counts of all the n-grams in some kind of dictionary. And you're also going to need to store all the counts of the n-1 grams. Because remember, what you have to do is you have to consider every word in the sequence and say, what is the count of its history and what is the count of the history together with that word in the training data? So you're going to need some kind of table. The reason I had a negative reaction to a matrix is that a matrix is going to be really big. How many possible counts might you store for the n-grams? V to the n. That's going to be a lot of zeros because most of those you will never have seen. If you use a sparse matrix to store all these counts or some kind of tensor with the different positions in the history as the indices, it'll be very fast, but it will be huge. The memory will be huge. You might be able to, there might be a good sparse matrix data structure for this, but typically people use different kinds of dictionary, sparse dictionary kinds of representations. And you need a second one for the histories alone so that you can get this ratio. There are some really nice packages that were written, 15 plus years ago that you can still find that will help you implement n-grams if you ever need to do it. But basically, the interesting thing I think to say about n-grams that is like a deep lesson that's worth carrying forward is how do we choose n? So why were n-grams like 3 when I started my PhD and like 5 when I started as a faculty member? What happened? Any thoughts? It wasn't about the implementation. It wasn't about the data structures. People were pretty good at that stuff. And it wasn't really about compute. It was kind of about compute. It was not, nobody was using GPUs for any of this. Any thoughts on what changed in the early 2000s? Well, that's what I'm saying. The context length got bigger, but why? There was more data. That is the answer. The internet was growing. The internet was pretty small at the beginning. The amount of text people were using to build language models, in fact, people weren't even using the internet most of the time to build language models. Originally, they were using things like newspaper corpora. So basically what happened was people were using more and more data. And here's the story. If you want to have a longer context length, a longer n-gram history, then you're going to have more parameters because the number of parameters, the number of things you need to store grows exponentially with that history length. What is a parameter here? A parameter here is effectively one of those normalized counts. It's this guy. It's a probability of a next word v given a history h. And so you get exponentially more histories as histories get longer. Most of them will never be observed. So what's going to happen, no matter how big n is, you're going to have a lot of zeros, a lot of zero probability n-grams. We call this data sparsity. This is a bad kind of sparsity. And it's something you never really get away from in natural language processing. Increasingly, as you get longer and longer n, you get higher variance. The quality of your model depends more and more on the training data that you have and how much of it that you have. So a shorthand way of thinking about it is that as n gets bigger, I need more data. And so what happened was we had more data and people could try longer and longer n. And it was like, oh, look, now the 4-gram is working pretty well. Now the 5-gram is working pretty well. And so it was worth it. But in the early days, we didn't have enough data or we weren't using enough data to make an n-gram work well. Okay, so we're now at a point where I can give you this kind of crazy roadmap of what kinds of research things happen in language modeling. And I'm going to argue that it largely has not changed in the 15 or so years I've been giving this lecture at LXMLS. So let's start in the middle. You have a language model. And let's talk about some different things you can do to improve your language model. They're colored differently. So one of them is you can increase or improve your training data. Okay, so what was happening when I was a PhD student was people were throwing more data at language models. And what that tends to mean is that you get better generalization, which is good. But it also generally means you get higher computational cost. So as n got longer, people did have to be more and more clever about those data structures for indexing the training corpora. At some point, they started using kind of MapReduce architectures, and many CPUs, the data would be spread out across many different nodes, and there was a lot of parallelization, and it got more complicated and more costly, but not in the way we're thinking about today. Another thing you can do if you have a language model and you want to make it better is you can increase its capacity. And with n-gram models, the traditional way to do that was to make n bigger, have a longer history. Now your model can represent richer distributions. It can do a better job of modeling the data. That will be more costly computationally. It will mean you have more parameters. It will allow you to get a better fit to the training data. And maybe it will help you generalize better. Sometimes yes, sometimes no. Sometimes this will just lead you to overfit your training data. And that is what was happening in the late 90s when people experimented with longer n-grams. It's like, oh, wait, this is not so good. It's overfitting to the training data. It's getting creepy. It's memorizing the training data. It's not going to generalize well. The third thing I like to point to that you can do to improve a language model is to improve its inductive bias. So inductive bias is whatever your model already has baked into it before you start looking at the data. So in n-gram models, the inductive bias is the distant history does not matter. You must not even pay attention to it. You only get to look at the most recent words. Is that good inductive bias? From today's perspective, we say no, not so good. But comparing a bigram to a unigram or a trigram or a 5-gram to a unigram, it absolutely was an improvement. To say that you can depend on some history and you can depend on more and more of it was generally a good thing, especially if you had enough data. So all of these things, the amount and quality of your data, the capacity of the model, the inductive bias in the model, they all contribute to how well your model will generalize, potentially to how well you'll do on test perplexity, or more importantly, how well you'll do when you deploy your language model in a real application. But this idea that bigger language models trained on more data with greater capacity will do better in applications, this is an old idea. I remember talks about this in 2007. Google was making their statistical machine translation system better just by making the language model bigger and stronger. So it's an old story. Okay, we have a few more things to get to before we take a break. Yeah, go ahead.
Yeah, maybe if you just could go back to the previous slides. I had a question, maybe I didn't get that quite correctly. What's the difference between like increasing modeling capacity and improving inductive bias?
So sometimes these are at odds. So increasing model capacity is basically saying this model can represent distributions that the weaker one couldn't. I'm making a change in the model so that now it is more powerful. There's a wider set of things that it can represent. Inductive bias can actually work in the opposite direction. It can say, here's a fact about language. This never happens. So don't even bother representing distributions that allow this event to happen. So I'll give you an example that's not done now, but there was a period where it was people were very excited about this. Natural language has syntactic structure, just like code, right? Not just like code, because it's harder to explain. There's no spec. We don't actually have a perfect grammar of English, but English does have grammar. It does have syntax. We form sentences in particular ways. If you bake that into your model, if your model models the syntactic structure of the sentence, then that's inductive bias. And it may be narrowing the set of things your model can represent, but it may be doing it in a very helpful way and saving a lot of probability mass from things that are very unlikely.
So in a nutshell, it's more about what to take into account and what not to?
Yeah, it's sort of like what is your model going to prefer even before it looks at the data?
Okay, thank you so much.
Yeah, great question. Today, we don't talk a lot about inductive bias in language modeling at all. I would argue that most of the inductive bias is probably coming from things like the positional encodings in the transformer. If you have no idea what that is, just wait till tomorrow. And the tokenization method and a few other things. But there, people who study theory are hard at work trying to figure out what are the inductive biases of a transformer. We don't really have a good answer to that yet. Okay. So I said that a huge amount of energy went into these earlier days of language modeling, trying to prevent anything in the model from being zero. So remember I said data sparsity. Most of the n-grams you will never see. But yet you have to make sure they get a non-zero probability to make sure that perplexity stays meaningful, because you're going to see n-grams at test time that you never saw before. So what can you do? Well, I could talk about this for an hour and you would be bored out of your mind, because there was an extremely rich literature of different ways of trying to make sure that the probabilities were never zero. We called it smoothing. The simplest method is before you normalize the counts, add some fixed small quantity lambda, like 0.1 or 0.5 or something like that, to everything. And that's like okay, but it tends to probably smooth a little too much. So people came up with many methods. There was a method that was kind of like recognized as a good default called modified Kneser-Nye that came out in 1998, and that even today I still see people saying, "Oh, we compared to an n-gram model and we used modified Kneser-Nye." There were also things that people did with parallel computing that sort of like did some local calculations that gave you a number that felt like a probability, but it didn't properly sum to one. So the Google folks called it stupid backoff. It was like using embarrassing parallelism to smooth the language model in a way that didn't give you a proper probability distribution. But if you didn't care about perplexity, it was perfectly fine. And that was a nice solution that people liked for a while when they were really just evaluating on downstream systems like translation. But in general, I think thinking about smoothing and sort of pointing to it is a nice way to introduce this sort of problem that came up in Kyung-Hyun's talk actually last night. We may choose a general technical approach, like we're going to use n-grams, but there's a whole bunch of decisions that you still have to make after you do that are usually not especially interesting, but they matter a lot. So this could be the length of your history, or it could be the lambda that you use. What do you add to every count before you normalize? And these are examples of hyperparameters. They're choices that are important. You have to make. You can't avoid them. But they're not interesting. It's not like, oh, if only I'd known that n equals 6 was the magical solution, that would solve all my problems. It's not like anybody has a flash of insight when they learn about hyperparameter settings. It's like, oh yeah, you have to choose these values. And usually there's not a lot of like, rational reasons for choosing them. I think last night Cho used the word intuition, or people follow best practice from the previous paper. But a lot depends on how much energy people put into choosing their hyperparameters. So I'll give you the advice that you should treat this as an empirical problem. You try different values. You use a validation data set to choose the ones that you want. Never the training set, because what will happen if you use the training set is you'll always pick hyperparameter values that favor the training set, and you won't generalize. So with n-grams, classically, if you use the training set to choose your n-gram length, you'll always pick the longest one, because you can always fit the training data best with longer n-grams. But that doesn't necessarily generalize well. You also do not use the test set for this. As we've already said, that's cheating, and it came up in Kyung-Hyun's talk as well. You got to use a validation set, separate validation set for hyperparameters, always. I like to advise that you actually, and actually he did exactly the thing I advised, which is to use a systematic and replicable search, something like a randomized search. You define the space that you're going to search in, you report it, you do random search, so that if somebody else were to do the same thing, they would get similar results. We wrote a paper about this called Show Your Work now 6 years ago, basically arguing that people need to report more details about how they do hyperparameter search. It's the point is still there. Kyung-Hyun was making it last night. So this is maybe one like deep lesson you should keep with you after the summer school. When you're facing hyperparameters, you just have to say, all right, this is an empirical thing. I'm going to say what I'm going to do. I'm going to write it in the appendix of the paper so that I don't end up tricking myself into somehow coming up with a solution that's better than I would have gotten if I had been careful. Okay, so everything is kind of the same. The n-gram models in general are easy to understand, just like the unigram model. I don't think there's any deep leap of understanding to make sense of them. They're still pretty cheap. People wrote nice papers about how you could parallelize them and learn them very efficiently across many nodes with distributed data. In applications where data is scarce, I still think they're a great solution. But we don't love, they're still not linguistically accurate. They still have this kind of finite history. And this data sparseness problem leads to this nasty smoothing thing that you have to do. So around 2003, a new solution started popping up that was somewhat different. And people started talking about neural language models. So the word neural, I think, is confusing and unhelpful. I'm gonna try, I can't avoid using the term, but I think you have to kind of divorce it from any notion of the brain. This is not like brains at all. All we're gonna do is say, instead of doing a lookup for a word and a fixed length history, like this theta value in that big dictionary table thing, we're gonna define a vector function where we take some encoding of the input. That's your context from the first word all the way up to the most recent word. You're going to pass it into some encoding function, and then you're going to transform that into a probability distribution over the next word. So this transformation in neural net world, it's usually composed of it's a series of simple functions, usually alternating between something affine or linear, and then something nonlinear, and then repeat. And the form of that function has varied, and there's lots of different considerations here. But the basic idea is that instead of lookups, you're going to do encoding. So you're going to move into continuous representations of the relevant things. And you think of the probability distribution over the next word as just another continuous vector that happens to sum to 1. So what is a neural net? Again, the name is confusing. I like to think of it as a function that takes learned parameters and maps inputs to outputs given those parameters. And everything here, the inputs, the outputs, and the parameters are real valued vectors or matrices or tensors or collections of those. And the key thing that you pretty much always have 99.9% of the time in neural nets is that you can differentiate the loss function of the neural net with respect to the parameters. And there's some nonlinearity with respect to the data input. So we're representing weird functions that are hard to visualize and hard to understand. So nonlinear simply means that you cannot come up with a matrix that transposes the input into the output simply by matrix multiplication. There's going to be some more rich, interesting things going on inside that neural net. Okay, so what we're going to need to build our neural language model is two things. We're going to need an encoder that maps word histories to vectors or matrices. And we're going to then need a way to interpret the output as a probability distribution over the next word. So the very first version, I'm being a little bit contradictory here because people did not call this model a neural net, but it was very much an approach to language modeling that people tried. It's just think of the prediction of the next word as a classification problem. So let the label set be the vocabulary, and think of training a supervised classifier that takes instances of histories as input and then maps to the next word, and you're trying to predict the next word. Or maybe a distribution over the next words. Many classifiers are probabilistic and work in that way. So you can find this idea for language modeling going back to the early 90s. It's a little different from the traditional classification setup that you learn in a machine learning class, where you assume that all of your training instances are independent. Here, they're all overlapping because it's history and then the next word, and then that word immediately becomes part of the history. But you can still apply the same principles. It's fine. And so one way to do this is multinomial logistic regression. Did Mario talk about that yesterday? Yes, okay. So here is in probably different notation because everybody uses different symbols for multinomial logistic regression. Here is language modeling with a finite n-gram type history as a multinomial logistic regression classifier. So you have some feature vector of your history and your words, and you take an inner product of that with some weights. Those are your parameters. You exponentiate it, you normalize, and now you have a probability distribution over the next word. One immediate and beautiful consequence of doing things this way is that this function, which is known as softmax, when you consider it as a vector over all the words, modulo the problem of underflow, it will never give you a 0, because exponential is going to always give you a strictly positive output. So if we think of this as operating on real numbers, and we don't worry about floating point arithmetic, then you will never have a 0. You will always give a little bit of probability to everything, as long as these features and weights are finite. But what you have to do if you do this is you have to decide what features of the history and each candidate next word you're going to use. And so the literature around this kind of approach to language modeling was really a lot of thinking about what kinds of features make sense. And people sometimes derisively use the word handcrafted, but really it was like you would write templates and you would say these are the kinds of things that matter for predicting the next word. Sometimes people tried to put in linguistic things like syntactic cues. Often they had features associated just with the specific surface word patterns themselves. The thing that made this pretty challenging was that in the 90s, when this stuff was being developed, the computational cost of training and doing inference with these models was just huge, because you have to normalize over the vocabulary at every step, and this was just a nasty operation. Also, people did not call these neural nets. So again, I'm being a little bit expansive in saying that these are the first kinds of neural language models. But if you look at this, I would argue this is a nonlinear. This is linear, and then this softmax is a nonlinearity. So it's sort of like the simplest one-layer kind of neural net you could have. There's a question over here. You want to shout? Oh, here he comes. How does it handle different lengths of sentences? The same way every language model does. This is only giving you the probability of the next word. And so you only normalize over the vocabulary. It's locally normalized, if that makes sense. So remember, you can take the probability of the whole sequence and decompose it into the probability of each word given its history.
So we take like each word individually.
So you take each
independent.
That's right. Not independent, because it's conditioned on the previous words, but it's decomposed into a conditional probability of each word given that history.
But when you say condition on, is it like condition on the immediate previous word?
Yes, the immediate previous n-1 words, just like an n-gram model.
But n being n the length of the sentence?
No, n being little n being a fixed number like 5 that you choose.
Okay, so there is kind of still n like
This is still an n-gram model. Yes.
Okay, thank you.
Yes.
Okay, thank you.
There was, now that you mention it, there was a variant, which I think they called it whole sentence maximum entropy models, where the idea was that you did not decompose this way. You had features over the whole sequence, and you normalized over all possible sequences everywhere. And you could never calculate that computationally. That's not tractable. And so you had to resort to approximate methods. And that was computationally, it was very beautiful, but it did not work in practice. It was too computationally expensive. But that was around 1999. Whole sentence maximum entropy language model, Rosenfeld. Yeah. So the other thing to say about this was that at this time, the algorithms weren't quite mature. So people were still figuring out how do you optimize, how do you minimize the cross entropy loss or the maximize the log likelihood when you have a model like this. And today we look at it and we say, oh, it's a computation graph. You just take the derivatives and do SGD. But back then, the default assumption was like, oh, well, they recognized that this was convex optimization. And so they went to the convex optimization literature and they found that there were algorithms like, gradient descent being the first one, but then, many others like conjugate gradient and LMVM. There were a whole bunch of these algorithms, but they were like the number of parameters was way bigger than what the applied mathematicians had been thinking about. And so it like wasn't a practical solution at first. So they came up with all kinds of specialized algorithms specifically to try to minimize the loss for these functions. And if you read this literature, it's fascinating, the ideas people were having. A lot of the time it was like coordinate-wise, choose one weight and then cycle through, all kinds of different things. Eventually, around 2006, 2007, people kind of landed on SGD or variants of SGD. And it was such a relief. It was like, oh, there's a nice algorithm that scales, that converges fairly quickly. And it's pretty efficient and it's pretty easy to solve. But it took some time. So like all the pieces didn't come together all at once. It's kind of interesting. We talked about why these were impractical because of this denominator. For every word, you had to calculate this sum, and you had to calculate the features over all possible words that were alternatives. It was not very nice. Today, it might not be so bad. We might be able to come up with clever tricks for it, but back then it was bad. Okay, we're at our stopping point. So you've now seen your first quote unquote neural language model, multinomial logistic regression. I think it's a powerful starting point to help you understand the principles and appreciate how we landed where we are. The models that are coming, we're going to have a whole zoo of more powerful things that are creeping closer and closer to what we use today. So go have some coffee and we'll come back in at 11? 11. Cool. I'm going to go ahead and get started because I don't want us to run over too much. People start getting hungry. What we're going to do with the rest of the time is we're going to see a range of different neural network approaches to language modeling, and then we're going to talk about some ways language models have been used. You're going to see a lot of different techniques here, and I think I tend to hate lectures that are like, here's a thing, here's another thing, here's another thing, and here's another thing. The point isn't for you to remember all the details, and in fact, I'm not even going to give you all the details about these different ways of building neural language models. I want you to get the high-level intuitions, and I want you to see the similarities and differences, because I think there's a lot more to be learned from seeing how things change and why things change, and that will help you adapt to new developments and make sense of what you're going to see tomorrow. So the two key developments that got us to neural language models as a competitive solution, fortunately, they're both pretty easy to understand. The first one is the idea of embedding words, thinking of words not as discrete elements of a vocabulary, but rather as vectors. And the second one is layering so that your model gets better capacity or better effective capacity. That is, the set of distributions that can be represented or that can be learned seems to improve as we add more layers. So you can think of both of these together as giving us the modern neural language model. And the good news is we don't have to talk a lot about some things. The idea of using stochastic gradient descent to maximize likelihood, that stays the same. The only thing that's really different is that for the model we talked about, the multinomial logistic regression model we talked about, that one has a really nice property, which is that the likelihood loss is convex in the parameters. So it doesn't really matter how you initialize. If you run SGD long enough, you'll get close to the minimum, and you'll get a good solution. That is not the case with neural nets in general. They are not convex, and so initialization may matter. We're not going to spend a lot of time talking about these issues because today they don't create a lot of practical concern, and I don't think we really fully understand why it's okay, but we're not going to stress about things that we don't need to stress about here. Let's talk about vectors, word vectors. The starting point for word vectors is to assign to every word what we call a one-hot vector. So if we have V words in our vocabulary, we can arbitrarily assign them indices, and then for the first word, we'll let its one-hot vector be 1 in the first position, and the rest are all zeros. The second word will have a 1 in the second position, and the rest zeros, and so on. So we have V distinct orthogonal one-hot vectors, 1 for each word in the vocabulary. And so the way that a neural language model pretty much always starts out is by looking up each of these history words, each of the words that you're conditioning on in the history, and multiplying its one-hot vector by this matrix M. And what M is going to do is it's going to take this V-dimensional one-hot vector and return something smaller, something of dimension D, which is, I don't know, 100, 1,000, something in that range, much smaller than the vocabulary. And it's sometimes called a dense representation. It's one little slice out of that embedding matrix M, which gives you a vector for every word in the vocabulary. So we call this the embedding, or we call it a word vector. And this is sort of the key first thing that you need to make language models work. And so where does M come from? Well, today, pretty much always, it's just another part of the parameters of the model. So you learn M alongside everything else by SGD. You initialize it in a particular way with a little random noise. And then as you train your language model, the model learns how it's going to embed every word. And that's kind of like the spiritual thing about neural nets in general is you don't put a lot of energy into designing representations. You let the model figure it out just by following the gradients. What representations are going to help me do really well on my task? In this case, the task of predicting the next word. But this idea of dense word vectors, as opposed to the one-hot sparse word vectors, leads to this really kind of fascinating idea. And the research community was really fascinated with this for about 5 years. Words can live in this high-dimensional space, this continuous space, and they can be closer or farther. And many people got very excited about what happens if you build, if you learn word vectors. How does that relate to the meanings of words? And they find things like words with similar meanings tend to be closer together in the space. But this is, I don't know, this word vector thing is actually a little bit older than neural language models. And we need them. We need word vectors for neural language models, but the idea is older. The older, lots of things kind of get reinvented or resurrected in new forms. So the idea of word vectors goes back to like the early 90s, and it had nothing to do with language model at all. It was just like a completely different way of thinking about language and computation. And in fact, there's a different way I could have structured this lecture, which is to start from word vectors and work up to language models. And if you want to explore kind of that series of connections and how they relate, I have a paper that was in CACM about 5 years ago called something like Putting Words into Computers or something like that. It's another kind of semi-broad audience, not super mathy survey and an introduction to the topic, because word vectors and contextual word embeddings were starting to become really important at that time. That was slightly before large language models. So anyway, you can look in literature and you can find standalone methods for estimating word vectors. And they usually would start with co-occurrence statistics, like how often does word V appear just before word V prime? And you would ask questions like, does this happen more often than you would expect by chance under a simple unigram language model? Or relatedly, you could set it up as a classification problem, like here's a word at one position, guess what word will occur in some nearby position. And so this kind of thinking led to very simple probabilistic models like the skipgram, which widely released and used Word2Vec package implements it. Basically, you can think of these as neural classifiers very much related to taking a co-occurrence statistics matrix of all the words by all the words and doing some kind of matrix factorization or dimensionality reduction on it. And what you would get out would be these word vectors. We don't use these so much anymore. Now we usually just treat that embedding matrix as just more parameters, initialized randomly, train it during language model training alongside everything else in your language model. But there was this idea of using a different algorithm like skipgram, which was relatively cheap, plug those in and then freeze them as some of the parameters of your model and then continue learning the other language model parameters. Or you could continue fine-tuning them. These terms pre-train and fine-tune, this is how they were originally used in NLP. You had your word vectors and they were pre-trained and possibly fine-tuned. And why? Why not just train it all end to end? Well, remember that people are often limited by computation. So if you could get really good word embeddings at the beginning cheaply, then maybe it would be faster to converge on a good language model later on. And that might actually even still be true. It's just that today we've sort of given up on that idea and we assume it's probably better to learn everything end to end from scratch. But that idea is still there, and there might be a point at which it comes back. I don't know. Okay, so when we're doing language modeling, though, we're thinking about sequences of words. So now that means sequences of vectors. Remember, everything in neural nets is continuous. The inputs, the outputs, and all the parameters and the transformations and intermediate quantities that we calculate. So what we're gonna need to deal with in NLP in general and in language modeling is variable length input. And that's the thing that's kind of always been a sticking point for traditional neural nets. Neural nets like to think about like an image coming in and the image being a fixed size, fixed dimensions, and whatever processing happens can kind of assume everything is fixed length. But language sequences can be arbitrary length. And so that's kind of the thing that makes things tricky for doing neural language modeling. I said the other piece was to start adding layers. So again, neural networks pretty consistently are built by composing a mix of two kinds of functions. Affine ones, which have parameters, and these basically take a vector like V, transform it by multiplying it by a matrix, adding some bias vector, and then you get a new vector. And that might be the same dimensionality or different. And these parameters, the W and the B, are just learned alongside everything else in the model through SGD. You learned about this yesterday. And typically these affine transformations are interspersed with nonlinear transformations like softmax, which we saw earlier, element-wise hyperbolic tangent, rectified linear units. You can probably name 3 or 4 more that have become popular. And these typically take an infinite domain of inputs and squash them into a finite range like this tan H here between -1 and 1 or 0 and 1, or maybe they just squash on one side like a ReLU, but they do something nonlinear, and that seems to be really important for neural nets to be successful. And you can kind of understand why. If we had no nonlinearities, if everything was affine, then the whole thing would just be a linear transformation. And it's not clear that you'd have much expressive power. So typically you see affine, nonlinear, affine, nonlinear, affine, nonlinear. And the typical story that we hear, and there are even some proofs about this, is that adding more layers will increase the capacity of what your model can represent or what it can learn. And so that means more layers means more parameters. It means more computational cost, but probably better training data fit, and maybe if things go well, better generalization. So that just kind of puts us back in this mindset. So you can think about adding more layers as going here. And I would say moving to word vectors is a change to the inductive bias of the model. It's now saying something about words. It's saying words or I should say vocabulary items, because they could be subwords. They can have relationships to each other. They can be closer or farther apart. I actually think this is an often overlooked piece of the story, that continuous representations of words, where words can be nearer or farther apart from each other or more or less similar, where words can share statistical strength. When you learn something about one word, you're also learning things about all of its neighbors, all the words that are similar to it, that are close to it in that vector space. I think that's extremely important to the inductive bias and a big part of why neural language models have been so successful. So it's now 2003, and this is the first language model, I think, that used the term neural. It was a feed-forward neural network. It's still an n-gram model. I know it looks crazy. I tried to add some colors and things to make it a little less hard to look at. Everything that's in pink is a parameter. And the word, you can see the word embeddings here, M. Those are slices of my embedding matrix. The hyperparameters that you have to choose for this are two different dimensionalities, D and H. And I want you to notice that if you start from the inside out, you have you're starting with a word vector here. You go through an affine transformation. Then there's a tanh nonlinearity. Then there's an affine transformation again, which brings back another copy of the word vectors. Notice that we're summing over the different positions in the history. So this is an n-gram probability because it only looks at n-1 previous words. And you have different parameters associated with each of those positions. So this is A sub j means in the jth position back from the current one I'm trying to predict. So there's another affine, and then finally the softmax is your last nonlinearity. So it's basically two layers. This was a very interesting model. Here's a picture of the computation graph. This is the 6-gram version of the model. So these are the 5 words in the history being mapped to word vectors. They go through an affine transformation. They go through another affine transformation. This one goes through a tanh. These two things get combined. And then the softmax at the end. I put all the parameters in here on the arrows to show you what's getting multiplied and added in. But it's, there's your computation graph. Not super complicated by today's standards. People tried to talk about what was going on in this model. Back then, we liked to think about features. And so, we would say, well, you've got these word embeddings of the context words are kind of like features, not interpretable features, just features. And then we transform them and we get new features by combining them with their neighbors and the parameters weight things differently. You can't look at any one parameter in this model and interpret it at all. You could with multinomial logistic regression, right? You could look at the weight associated with a feature and say, this tells you how a change in the feature value will affect the probability. You can't really do that with these nonlinear models. So you've definitely given something up. But what have you gained? You've gained something really nice. We think of neural nets as being huge and having large numbers of parameters. But what's crazy here is that even with a fairly large vocabulary of about 18,000, and some various settings of the parameters, they basically show that the number of parameters in this model is about 400 times v plus a constant of 30,000. Compare that to v to the n, which is effectively the number of parameters you have in an n-gram model. This is potentially very efficient. And they did some ablations. They tried forcing the A matrix to 0 and eliminating 300 times v of the parameters, which is actually most of them. And they found that it actually performed a bit better, kind of crazy, but it was slower to learn. So there's often these trade-offs between quality and efficiency. They also did some things like average, instead of concatenating the different word vectors together before matrixing them, they tried averaging them, and that was another variant that was somewhat smaller. The paper had a lot of different ideas in it, but interestingly, I don't think I have this in the slides. It was actually quite expensive at the time, even though it has a lot less parameters, because you had to do SGD. You had to repeatedly update each of those parameters. You can't just count and normalize. And so it didn't really catch on. It was just sort of like, interesting, something new, but it didn't become the norm yet. People didn't quite understand, and I'm honestly not sure we even understand now why it works. But they tended to say that it was working because it was learning new combinations of features. Every time you have a layer, you can combine features you already figured out and get new features. But we can't point to a feature and say what it is because none of it is interpretable. But what they're doing, what's happening here, some people tried to relate it to the search for good features, which was a big part of the sort of linear model days before neural nets. how do you develop good feature sets for getting good performance? You do a lot of search, but it was discrete search, and it was very expensive. Here you're doing a different kind of search. You're doing SGD, and every time you update the weights a little bit, you're updating the features a little bit, and you're doing a smooth search for better features. Today, we would probably not talk about features. We'd just say you have representations of words, you have representations of histories. These are calculated through the use of many different parameters, and you're tuning all of them in parallel at the same time to be really good at the next word prediction task across a lot of data. So this was the start of getting word embeddings and continuous representations of words into NLP and language models. And the good news is you just use SGD. You don't have to change very much. There are many tutorials on SGD. I'm sure it was covered yesterday in some detail. You can find many different versions of this, many lectures online. But the thing I always want to point out is SGD doesn't really have any guarantees when you have a non-convex function like the likelihood you're dealing with here. So whenever you are doing a perplexity experiment or evaluating the model, you're really evaluating the initial values you chose, or your method for choosing the initial parameters, and the algorithm that you use to update them and estimate. And both of those two things are now connected. So there's more room for variation. If you run the same thing again with a different set of random initial points, you might get a better or worse answer. Also, this was an incredibly expensive model on CPUs. So they were using 40 CPUs, which was about, I don't know, that was like a lot at the time, and it took 3 weeks. I remember running experiments of roughly that scale, and you were really depressed when they got messed up, and you pissed off all the other grad students in the lab when you did it. So this was not a practical solution yet. Let's talk about this model a little bit. It's funny, there's absolutely nothing, no inductive bias in this model that tells the learner that the most recent word is closer than the earlier ones. It has to figure that out on its own, but it probably does, right? If it looks at enough examples, it's eventually going to learn like, hey, I should pay a lot of attention to that word that came right before me and a little bit of attention to the things that came farther back. You have more hyperparameters. So in n-gram days, you had n and maybe some smoothing things. Here you have to pick the dimensionalities of the different parts of the model, and they tried different values in the paper, but only a few. Can't interpret the models at all. Parameters mean nothing on their own. Not even the word vectors, like you can't look at a word vector. The only way to interpret a word vector is relative to other word vectors. Architecture, I don't know. Does this look intuitive to you? I mean, you know, I remember looking at this paper and being like, I don't know. Nowadays, it looks relatively simple, right, compared to some of the things we see. But it got good perplexity reduction. And so it got people interested, and people started, you know, there was steady work on neural language models from that time. And so, I don't know, like compared to the cute little kitten, this is like a fatter version, harder to understand, a little bit more confusing, but moving in a good direction. So I don't know, let's reflect a little bit. If we had an input that was bounded in length and we really believed in n-grams, then this whole thing would make sense. But that's not really how language works, right? There's nothing special about the word 4 positions back. That feed-forward model is literally learning parameters for what do I do with the word 4 positions in the past. It doesn't scale to longer sequence as well, right? Imagine that we wanted to scale this up and have histories of 1,000. You're now going to have parameters tied to 974 words back. That is specific parameters for that specific position. It doesn't make sense. It also doesn't capture the way words tend to combine locally with their neighbors to form bigger meanings. There's no notion of compositionality here. Everything is just this sort of fixed template. So what we're going to talk about next are some styles of networks that reuse parameters to encode the sequence, regardless of its length. So we're basically going to stop making the n-gram assumption and say what we have is an arbitrary length sequence, and what we have to do is come up with a way to encode it in a fixed vector. And so one solution to this is called the convolutional network. And this was very, very popular and continues to be very popular in computer vision. The word convolutional, whenever I see it, I just think it means sliding window. Okay. So you're going to take the entire history all the way up from word 1 up through t-1. There's no Markov assumption. You're going to stack all of those words into a matrix by taking their word vectors and just lining them all up next to each other. Call that x0. And what you're going to do in the ConvNet, at each layer of the network, you're going to calculate a new matrix XL by applying a convolution function to the matrix in the layer before. And that vector, you can think of that the vector at the last position there of that matrix as being a hidden state representation of history word M with all of its context at layer L. And so you can use that then to predict the next word. So here's a little bit of math. The idea is that at each step, you're going to apply affine plus nonlinear sliding window functions across the input matrix at each position. And so here's my nonlinearity. I'm being abstract. I'm just calling it F, but you could make it a tanh. And you have to choose a width of the sliding window. So everything you're doing is going to look at a local chunk, but it's going to migrate along the whole sequence and calculate features at each layer. I think I have a picture next. You have to choose the number of layers, you have to choose the nonlinearity, you have to choose the width, you have to choose the number of filters. But the basic idea is here are your 3 different filters. You're going to apply them to this, this window of 3 words. You're going to get some part of the matrix of the first vector in the next matrix by applying the convolution. And then you're going to move to the next position. And you're just going to slide the window along and calculate each chunk of that output matrix as you go. So it's the same idea, nonlinearities applied to an affine transformation at every layer, and you decide how many layers. Each one is called a convolution. And then at the end, you can take this whole set of, I like to think of each of these as like a new representation of each of the words in the history, and then I can pool them together to get my final representation of the state. And what is pooling? Pooling could be an element-wise max. It could be an average. It usually has no parameters. It's usually a very simple function that takes the matrix and gets you back down to a single vector. And if you set your dimensionalities right, that final vector can have a dimensionality vocabulary length. And so you can apply a softmax. And now finally, you have a distribution over words. And so this is a way to build a ConvNet language model. And in fact, people did it a little bit. I don't know. There's something really cool about this. I hope you saw it. Let me show you I'm going to walk through this again just so you can get it into your head. And then I want to see if you can answer the question. So basically, I'm going to keep doing this thing at each step and store it in the matrix at the next layer. And I do that at every layer. And if I have this matrix, then I can calculate the representation of the whole state and make my prediction about the next word. If I'm moving left to right and making predictions about one word after another or generating from the model, consider the computation I did for encoding the history of word xt, and now consider the computation I have to do for the history of word xt plus 1. Do you see anything you can do that will make this efficient? You can do a lot in parallel, yeah. The point I want you to see is a little simpler than that. Imagine that I'm moving on to the next word. Most of the computation I need at this layer has already been done for the previous word. All I have to do is calculate this one new vector that I'm going to tack on at the end. Most of the work for building this matrix was already done with the history. So in other words, I have a constant amount of work per word. I don't have to go all the way back to the beginning and re-encode everything. That was not the case with the feed-forward network. I had to pass all of the even though the history was finite, I had to pass in all the history words again for each word because they occupied different positions as I step forward. So computationally, this is really, really wonderful. Constant amount of work, relatively small amount of work for each thing. Even the pooling, right? If I just add a new vector on here, redoing the pooling should be a relatively simple operation. I'm either adding in another vector to the average or I just take another element-wise max. So these originally came out of computer vision. They also, something very similar with a different name emerged in speech recognition. These were used in NLP for text classification. There were some papers that applied them to language modeling. Never really caught on. I think, I think it's basically because other things seemed to work better. But they were compelling. People also did things like varied the way the convolutions work, so you could take longer steps at deeper levels and try to get increasingly long histories effectively. So you can find nice papers studying how to get longer windows. But this wasn't really, it's not really languagey. These were really designed for learning how to process images, how to get good representations of images to do things like object recognition. So they're fast. They're very fast, and they're very amenable to parallelization, as you pointed out. But they never quite made it in NLP. It was just it's kind of a side note. So I like to mention them just to kind of say, so you can see, wonder why this, why not that. I think the next thing makes it a little more clear why it's stuck. But anyway, it's nice to know some things that could have had a chance, maybe could come back. You could imagine convolution layers making their way back into modern language models at some point. Any questions? Over here.
Last 2 weeks ago, I think I read the paper. I tried to review it, and they tried to train new language model with new technique. They used other language model to detect the redundant data, the similar data, to remove them to have a better language model. Is it possible?
I mean, it sounds like you read a paper doing it, so it must be possible.
No. I mean, it's under review, not accepted. I should.
Okay.
Yeah. But I think they try to remove the information about frequency of different information by decreasing the size of data set to have a faster training.
Oh, I see. So like basically cull down the training data and see if you can learn just as good a model from less data.
Yeah.
Yeah, I mean, it could be. I think, there are people who say a lot of the data we train on is low quality or unnecessary or redundant, and maybe you can do just as well by training on less. We certainly do a lot of filtering when we put together our data sets. I think the idea of quality is very tricky to define. And I tend to stay away from very general notions of quality. I think it's like, well, what do you want to build? If you want to build a chatbot, then some kinds of text are not helpful and others are. And the story is completely different if you want to build a tool that can summarize scientific literature. So I can definitely believe that there are ways to get better efficiency by culling down the training data. But sounds interesting. I don't know. I haven't read the paper.
Because they use this.
They used a ConvNet.
No, they use this model to test different downstream tasks. So that in most of the tasks it had better results.
Cool. Yeah, I hope they didn't use the test data.
Yeah.
To make decisions about the model.
So thank you.
Yeah. Another one down here.
So this convolutional model that you were just showing, like how does it, like what happens when you have like longer sequences, because like what I can imagine is like if you have like a pooling operation, it's gonna like the information, it's gonna dilute,
It's gonna dilute. Yeah. You're never gonna get, I think short of the transformer, not to steal the thunder of tomorrow's lecture, anything you do that sort of doing a computation across the whole sequence that's sort of systematic and doesn't have the flexibility of attention, you're probably going to pay less. You're probably going to like lose more and more information from the left side. And I think you can actually show with the ConvNet up to the pooling, basically at some point you're not you've forgotten. Your intermediate values are not dependent on the history past a certain window. It effectively has a fixed window. So that's the problem. Like, how much do I retain? How do I teach the model to retain the right amount of information from the distant past? Because there's something there. We know that being able to access very long histories is useful. But how do you teach the model to make the most of that and still make good predictions using local information? That's the challenge.
Sorry, can I ask a question? Sorry. everyone was kind of. Basically, there's this field already, like the data compression, to be able to like encode the most amount of information in the shortest amount of sequences. And I was wondering, in the convolutions kind of reminded me of LZ77, that is a compression algorithm. And I was wondering if those compression algorithms could actually help large language models. And yeah, that's my question.
I don't know. I feel like I have seen people applying compression algorithms to the data before passing the data through the neural net. I haven't followed this stuff, so I don't want to say more than that. I think people have thought about it. There's a sense, there's an argument that what's happening when you're learning is you're learning to compress. And I don't know if that position is particularly helpful because, you know, there's no proof that it's optimal or anything like that. It's just sort of like striving to do a good job of prediction through compression and getting good representations. There is probably some deeper connection that I'm not aware of.
Also, another question: are hash tables and those types of more advanced data structures being currently used, like in language models? This is just out of curiosity.
Are hash tables being used
Yes.
in language models?
No, they are not being used.
I don't
currently.
think, I mean, I'm
Just
not,
in n-grams.
I'm pretty far from the code these days, but I'm pretty sure that almost everything that happens in PyTorch is like after that first lookup, it's like matrix and vector multiplication as much as possible because you want to maximize, it's all now designed around the hardware, which is GPUs, right? So you basically want to squeeze the data through the GPUs as much as you can. And everything is numerical processing as much as it can be.
Thank you.
Yeah. Okay, great questions all over the place, but I love it. So let's move on. Let's talk about recurrent neural nets, because these actually had a serious moment. So every other version of neural language models that I talked about up till now, it was like, oh, interesting, kind of had a moment, didn't really take off. These really took off, and these were the going thing for a long time. And they're very easy to understand. I think, you know, you really appreciate them after you've seen these other things where compromises were made. Here it's I don't know. After some years of reflection, it's like this is a really good idea. So recurrent neural nets were born in the 90s, but they didn't really make their way into NLP until around 2010. And here the idea, I don't know, it fits language more nicely, I think. Tell me if you agree. There's no Markov assumption. The history for word T is the entire history going all the way back to the beginning. And we're going to map those to vectors. And what we're going to do is we're going to encode the history as a fixed length state vector, st-1. So that's the history up to and including word t-1. So at the very beginning, we set that to be 0, or maybe a learned parameter vector, but let's just say 0 to keep it simple. And then we have a way of computing the state given the next word using a recurrence. So the next word is going to be xi. We're going to get its word vector. We're going to multiply that by some parameters. We're going to take the state from the previous time step and multiply it by some parameters, add some bias, and that is our affine transformation. And then we pass this through a sigmoid, and now we get a new state vector. And so you can think of the state vector as being, it's not exactly ones and zeros, but sigmoids do tend to kind of map things more to the extremes. So you have values between 0 and 1, and at every time step, you read another word and you calculate this new state vector. And if you want to predict the next word, you take the state vector and you pass it through another layer. You pass it through more parameters and a softmax, and this U matrix reshapes it, so it's now vocabulary length. Pass that through a softmax, and that gives you YT, which is your distribution over word T. So simple. This was, I should say, this is the absolute simplest recurrent neural net. It didn't work very well. To make it work better, people had to do some more things. We'll talk a little bit about that. But the basic idea that you have this one function, this one little recurrence, and you just, every time you read a new word, you grind through and do the same thing, reuse the same parameters over and over, combined with the previous state. That state is it is all the information you have about the past. It's now encoded in this fixed finite vector. I don't know, very elegant, very simple. Notice that as your sequence gets longer, the network is getting deeper because the state that you're calculating at time step t has gone through one layer of this function at every time step. So the depth is changing with the length of the sequence. So this is one layer of the RNN getting you from a word. Here's a word coming in. Here's the previous round state vector. You go through your affine transformations. You go through the sigmoid. And then you can get your softmax here to get the distribution over the next word y. You also get the next state to move on to the next round. And if you unroll it, this is what it starts to look like. You're doing the same thing over and over at each time step. So that's the simple RNN. It doesn't work. There are two problems that it has. The first one is that the gradients tend to vanish. As you go back through that long computation graph, what you start to get is a lot of zeros. A lot of the parameters start getting sort of unaffected by things that happen in the long future. So it's just really hard to pass error back through those many layers. Also, the state tends to change a lot on each iteration. Basically, there's no mechanism for remembering the distant past. And so a lot of what people tried to do was improve what these things could learn. And the two main things they did were stacking to make deeper networks. So in this sense, you would have you would pass this state through another round of recurrence. And you'd have sort of two recurrences going in two different layers, or three or more. And you'd have separate parameters at each layer. And you could basically learn richer and richer transformations of these states as you went from word to word. That was one. Sort of familiar. Add more layers. It makes your model potentially more powerful. But the really important one was an old idea called long short-term memory. I'm not going to teach this. I have a whole lecture on it that I teach at UW when I have a whole 10 weeks, but today I only have 3 hours. So I won't teach you the LSTM, but the basic idea is to use gates. So you have these extra parameters devoted to learning how much to forget and how much to remember. What should I pass forward at each position in each of these state vectors? And so they're kind of hard to understand the first time you look at them, and maybe like the 20th time you look at them, you start to develop some intuition. But they're basically making they're like little 0, 1 type, sigmoid outputs that are close to 0 or 1 that decide, keep this, delete that, keep this, delete that, and pass bits of information forward. Of course, none of them are interpretable bits, right? It's a neural network, but it's learning. Some information gets forgotten and some information gets kept and repeatedly added back in. So that was it. The LSTM-based neural language model and LSTM-based representations for all other NLP tasks became the dominant thing for several years. And this was, like the 3-layer bidirectional LSTM was a way of learning features for pretty much anything. People would pre-train them on different things. And then tune them to particular tasks, and it set forward a big leap in performance, and it was advances on those that led to the transformer. So if we were to finish the lecture and go all the way through, we'd add another layer, and I'd talk about the transformer. But we're going to leave that for tomorrow's lecture. What I want to point out, though, is that none of these were really particularly, maybe the recurrent neural net starts to be kind of language inspired because it really is meant for sequences of arbitrary length. But what we're seeing is, I think, improvements in inductive bias, improvements in making assumptions about how language works. The idea that you want to encode everything in the past, you want to have an arbitrarily long history. Language really does come in a sequence. The processing has to be local and reasonably fast because we process natural language in real time. I think we're seeing an increased sophistication, and the transformer takes it yet one more layer. But they're also getting more and more expensive. So the RNNs, if you can believe it, people were complaining about the computation that you needed to deal with RNNs well before the transformer and well before we were using GPUs. In fact, the RNN is not a good fit for the GPU. You can't easily parallelize most of that computation. You really have to wait for each word to come in before you can process it. There are some modern things that look like RNNs that have rearranged the computation and maybe are starting to make it more parallelizable, called state space models. But those are still not quite there as far as I can tell. Okay, so I don't have time to teach the transformer. That came out in 2017. I want to talk about a couple of other abstractions around language models that are useful to know about and fit into the ecosystem, but they're not changes to how the model works. I'm done talking about the architectures and the gates and the nonlinearities and all that stuff. We're going to pop up to a higher level. So we've been focusing on this task of modeling the next word's distribution given the history and how you can compose those to get a full distribution over the sequence. So this is great for autocomplete, but what if we have an input? What if we have a sequence that we want to map to another sequence? So this comes up when a lot of the time today people talk about encoder-decoder models. What we've been covering is sometimes called decoder only because it just has one sequence. It just decode. You could just say sample and it would generate the whole sequence. It would just decode. Encoder-decoder has two random variables. There's an X input and then you're generating Y as an output. And they're both sequences maybe. And the driving application for this was automatic translation. Okay. So this family of approaches was developed for machine translation and we'll focus on that use case. But it has been applied to many other problems. And so it's an easy starting point for thinking about many things in NLP. So again, just like with language modeling, before I talk about a problem, I like to talk a little bit about how we evaluate. And there are sort of two aspects to good machine translation, at least two that I think are relevant to quality. Efficiency is a whole other thing. A good translation is going to be fluent in the target language, but also faithful to the original meaning. And so the way that people originally would measure this was with humans. That you'd take bilingual speakers and ask them, here are some inputs, here are some outputs. How faithful is this output to the input? And you could ask, you didn't need bilinguals, you could ask anyone fluent in the output language to judge fluency, but you'd basically get human judgments on the quality. Or you'd do comparisons. But around 25 years ago, people started saying, this is really expensive. If we want to iterate fast on this problem, we should really develop a way to automatically estimate the quality of the output. And so the first of these was called the BLEU score. I think Kyung-Hun talked about it last night. You basically have some human generated reference. So you have professional translators, or maybe multiple of them generate reference translations. And then you calculate something like a weighted average of different n-gram length precisions between the system output against the human references for different n-gram lengths. This was the simplest, earliest thing. There are many things that followed. I think Cho had a whole big slide. People still use the BLEU score sometimes. They probably shouldn't. Human evals, I still think, are probably better in most cases. But obviously slower and more expensive. So there's been a whole industry of developing better and better automatic evaluations. Some of them are reference-free. And that's usually what we accept as a way to measure progress on translation. So how do we solve translation? If you can believe it, people were thinking about this as early as computers started coming into wide use in cryptography and other problems. And so there's a famous quote from information theorist Warren Weaver saying, one naturally wonders if the problem of translation could be conceivably treated as a problem in cryptography. When I look at an article in Russian, I say this is really written in English, but it's been encoded in some strange symbols. I will now proceed to decode. In other words, the Russian speaker is actually thinking in English. And what came out is just sort of like this garbled up stuff that we just have to decode back. Nobody believes this is true, right? These are not the real assumptions that people have about language, but it's an incredibly useful way to think about the problem. And for a long time, this guided the way people built translation systems. So they use this abstraction called the noisy channel, where you assume if you have these two random variables, X and Y, and Y is the output, X is the input. So this is a little bit counterintuitive because they get generated in reverse. The story is that first, a source model generated the output Y, And then y went through a channel and got noised up and turned into something called x. And that's what we observe. Okay. So y was the plain text or the true message. It's the desired output of our system, and x is the ciphertext or the garbled up message, and it's the input that we have to process. So the decoding problem is to go backwards. It's to say what's the most likely y given that input x. And here we can apply Bayes' rule and rewrite that p of y given x as p of x given y times p of y divided by p of x. People know Bayes' rule. Okay. You can drop the p of x because this is all, it's a constant, x is given. And so what you're trying to do is choose a y that maximizes the product of the channel model. So this is a y that makes x likely, that is, it's faithful to x, and a y that is likely on its own, that is, it is fluent in the translation context. So successful translation means you want faithfulness to the input and fluency. So if we're mapping French into English, French input E, English output E, French input F, English output E, you want high faithfulness between E and F, and you want fluency in E. And in the original statistical formulations of translation, the fluency score was the language model. So we were using language models to translate, even in the 90s, but we used them alongside something else that gave us the faithfulness. And that was a very complicated model we're not going to have time to talk about today. We called it a translation model or a channel model. But the language model here, this was typically an n-gram model, trigram, 5-gram, something like that. And the translation problem benefited tremendously as language models were improving. You got better and better translation quality just by improving the source model, even for a fixed channel model. And the hard thing here was really, and I think continues to be, you always have limited data for learning this channel, learning the relationship between the English and the French, between the input and the output. This is easy, especially for English, because you only need unpaired text in the target language. So actually, let's talk about that for a second. The thing that allowed us to start treating machine translation as a machine learning problem was that if we had enough examples of French-English sentences paired, or pick any other language pair, then we could learn this translation model or channel model and couple it with a source language model to do the decoding. And all you needed was the data and a decoding algorithm and a good way to estimate this conditional distribution. Where do we get parallel data? Translation, what do you mean? So you need texts in 2 languages. Where do those come from? Parliament of Canada. Thank you. That was the original answer. The reason that this whole thing got started was some people at IBM realized that they could get a digital copy of the parliamentary proceedings of the Canadian government. Thank you, Canada. They do everything in English and French by law. And so these guys at IBM in the 90s got access to this collection of parliamentary texts. Do you think their translation models would be good for chat? No, because it's all parliamentary French and English, right? There have been other iterations. The European Parliament produces text, I think, in like 10 or 11 languages. That has become a big source of parallel text. There are some books that are translated. Books are tricky because of copyright. Can you use it? Tricky. Ask a lawyer. I was part of a project when I was an undergrad scraping the web to find web pages that were in multiple languages. That I believe is something that people have continued. Some religious texts have been translated into many languages, but again, the domain is going to be pretty different than, say, scientific writing or Wikipedia or other things. So the search for parallel data has been, people do produce it naturally, but finding it and finding usable data that's relevant to your target domain, that continues to be an important question, especially if you want to build translation systems that work for low resource languages. How do you get the data? That's the big challenge. Okay, so I'll just give you the brief history of MT. In the very old days, going back to Weaver in the 50s, people tried to build kind of rules, often based on linguistic theories, for translating from one language to another. If you've ever studied grammar of another language, you can imagine trying to write little regular expressions or table lookups or things even formal automata that transduce from one language to another. The whole thing changed in 93 when this noisy channel approach based on bitext, parallel text, was introduced. This stuff was very complicated. These were some of the first papers I read when I started in the field. And you think some papers are tough today. There was a lot of math in these papers, and a lot of details were not included, and it wasn't open source. They didn't share their code. No, not many people did back then. So there was an effort in the late 90s to try and re-implement all of that from scratch. That was one of my first projects. And then there was automatic evaluation, which sped things up tremendously. So open source, automatic, open evaluations, all good things. And then what happened, people started realizing the way these things worked was really word to word, mostly word to word translation. And a big part of it was learning the distribution over what words in English a French word would translate into, or vice versa. And people were realizing that going word to word was not working. You need more context. You need to look at what's happening around a word to know how to translate it. And so there were sort of two solutions that were in competition, friendly competition, I think. One was to start building kind of super words, right? Or phrases. Let's put chunks of words together and translate them as big blocks and figure out how to carve up the text into translatable chunks. This was called phrase-based translation. The other was more linguistically inspired, and it tried to use syntactic parse trees. So there was a lot of research in separate parts of the field on parsing, and people tried to use different kinds of parsing representations and trees to capture the abstract syntax of the sentences, and then use that to decide what chunks to translate. And so this was a thriving area up through the early 2000s. And meanwhile, in the background, people were starting to think about how to use neural nets to do this. And so I'm not going to give you all the play-by-play. There was some early work in the 90s. It really kind of emerged around 2014 as a viable approach. But they completely ditched the noisy channel. So they took a completely different approach. And so I now want you to erase your state history representation for the words encoder and decoder. They're going to take on a new meaning now. So the idea, and this should feel very familiar given what we did with neural language modeling, was that you needed to learn to encode the French, the input, and then you built a language model conditioned on that encoding that generated the English word by word. So it's conditioned now not just on the preceding English words, but also on your encoding of the French. And what's quite different from what we had before is that the encoding of the source is a deterministic function of the words in that sentence. There's not probabilistic reasoning here. We're not trying to follow Bayes' rule and decode and combine different things. We're basically encoding the source sentence and using that vector or matrix representation to help us learn what should come next. So the way this would often work is you would run, because you don't have to generate the word in the input. Oh, sorry. Here, my French is German. My input sequence is a German sentence. It's all the same to me. So you've got a forward RNN that works across and encodes each word in the German sentence, and you can also run one backwards and use the right context. Why not? We don't have to generate this sentence. This is just input. So we can do all kinds of things that are out of order, and we don't really need a probabilistic interpretation of any of this. We're just trying to encode each of the words in the input sequence. And what we get out is a matrix, which is as long, it has as many columns as it has input words, and arbitrary number of rows that gives you an encoding of each of the words in the input. We're getting close to the transformer, by the way. Basically, what happens is you're now going to use a recurrent neural net to define the decoder. But the recurrent neural net has access to one more thing. Remember, the old recurrent net had your preceding, your current input word, the input word right at this moment to help predict the next one. And it also had the state vector, which summarized everything in the past. You now have access to one more thing. You have this context, the encoding of the French sequence or the German sequence that came in, and you can access it in various ways. And so the idea of attention was actually born as a way to do random access on that matrix encoding of the source sentence. And it was originally introduced for recurrent neural nets. So again, I'm leaving out a lot of details, right? So like what kind of a nonlinearity am I using in the recurrence? What kind of nonlinearity am I using in the output? Probably a softmax. The key is that everything here is going to have, there's going to be parameters, there's going to be differentiability all the way back to the parameters. The access function I'm not going to talk about, but again, the word you should have in mind here is attention. Which French word should I look at to predict the next English word? That is what the model had to learn, essentially. So all of this is just a generalization of the kind of neural language model that we saw before, except now you've got this one more kind of object, this random access matrix representation of all of the input that you can look at. And they learned these things end to end. The whole thing is differentiable. And then for decoding, they use something called beam search. Does anybody know beam search? A few people. Does anybody want to teach it? Would the other people like me to teach it? I think this is, so we're going to close with an algorithm called beam search, which I think is like very useful to know because it's so widely used. And I think, you know, one of the topics people ask me, what should we work on in language modeling research? There's a lot of things that I think haven't really gotten the attention they deserve, especially with modern models. And I think tokenization is one. I think decoding is another one. So we're going to talk a little bit about beam search for sequence-to-sequence models. So I think this is almost the end. And then we'll have plenty of time for questions. So beam search is it's a greedy algorithm for trying to get a set of K hypotheses out of an autoregressive predictor. So you can use it for just a language model, but typically you're going to use it in a sequence-to-sequence setting or a language model with a prompt where you fed in some input and now the model is going to predict a sequence of tokens. And the dead simplest thing you can do is just pick the best token, plug it back in, pick the best token, plug it back in, and repeat, and just greedily choose each word in turn. Similar to that, you can randomly sample each word in turn, and maybe you can do that many times. Beam search is a little bit different because it's trying to find a set of high scoring hypotheses, and it's trying to be a little bit less greedy. So the idea is you choose your beam size K, which is the number of hypotheses you're going to finish with, and it's also the number of hypotheses you're going to keep at each time step as you move through and make your predictions. And typically, and so the main piece, the way the language model comes in is you have some kind of, you need a scoring function that tells you given this history so far, how good is each word that comes next? So we can use the log probability of the next word given the history and the encoding of the input if we have an input as well. And from here on, we'll just say we're going to score next words and you'll know what it means. You'll know that it comes from a language model. So you start off by setting beam B0, which is the beam at position 0, to be the set of all t-length prefixes that we're going to keep. And we only have one. It has a score of 0, and it's just a start symbol, meaning nothing has happened yet. We have not generated any words. And we're also going to keep a data structure F at each time step, which is the set of finished hypotheses of length up to the current length. And so it's empty. We have no finished hypotheses. So we're just going to step through time steps up to some max length. We often have a cutoff and say we're not going to generate more than M tokens. And we start off by saying we have no hypotheses at this length. We copy over the finished hypotheses. We keep all of them that we had from before. And we start off with an empty beam at time step T. And this is the real meat of the algorithm. We say, all right, for every hypothesis Y with score S from the previous iteration, so this is a partial hypothesis, this is a prefix of T-1 words, and every vocabulary item that could come next, we basically consider, let's score that next word, V, add it to the score of what we had before, so think of these as log probabilities, and tack on V to the end of Y, and put that in our local current iteration of hypotheses for length T. So if we have K things in BT minus 1, and we have V vocabulary words, then we're going to have K times V things in H. We're just going to consider every possible continuation of every hypothesis that we've had so far. And now what we're going to do, I like to think of H as a priority queue. So it's going to store these things in terms of their scores, and I'm going to repeatedly take the best thing out of H and consider what to do with it. And I'm going to do that until I have K hypotheses of length T and in the beam of time step T. So I pop one guy off. This is the best scoring hypothesis of length T at this time. If it doesn't end in a stop symbol, then I'm just going to add it to BT. This is now one of my hypotheses for position T. If it does end in a stop symbol, then I'm going to add it to my F data structure, my list of final hypotheses. And as soon as that final, that F sub T is greater than or equal to K, it has K things in it. I've got K complete hypotheses. I am done. I'm just going to return the top scoring item from FT or all K of them if I want K best. But if I'm not done, then I just keep going and I keep popping things off of H and putting them into BT if they're not done, putting them into FT if they are, until I'm finished. That's it. That's the whole thing. There are a few variations. There are a few tweaks to this. There are a couple ways you can improve it, but this is basically the core algorithm. And so this is a really useful tool if you are concerned about greedy search. And you have access to the probabilities coming out of your language model. You probably can't use this with an API-based model that won't give you the probabilities. So this is like if you're working with open models, you can do way more interesting things with decoding. Yeah.
How did you measure like the score again?
How do you measure the score?
Yeah, here.
Well, the score is you're summing up these log probabilities, so it is the probability of the Y sequence given the X.
So they're gonna be negative, right? So
They're gonna
assuming-
be negative. So,
so, like,
higher is better
you're-
though.
Yeah, so I mean, because like then this sort of like penalizes, like intrinsically penalizes like longer sequences, right?
Yes.
Because like you're only going to.
Yep, that's right. So this will penalize longer sequences, and this was a real issue in the old days with older language models. And so people would sometimes have like a way of trying to control for the length, like you would add something or subtract something depending on the length. We don't need to do this anymore. The language models have gotten pretty good.
But I mean, how did they solve that?
I think it's basically the models have learned that shorter is not always better because they have the whole history, right? So there's something in there there's something going on in the neural net that's like, oh, this is a pretty long French sentence. I probably shouldn't stop until I've really generated a lot of words. I think they've become more or less self-regulating. I don't see things about length penalties in the papers anymore. It's possible that they're still used in some cases.
Okay.
But yeah, it is definitely an issue with older like Ngram models.
Yeah.
Okay, so beam search, I don't know, very good thing to know about. The runtime will depend on the beam width. If you set K equal to 1, you're doing greedy search. You can show that this just reduces to greedy, pick the best. The runtime will also depend on the vocabulary size. So that's another reason smaller might be better, but the output length too. So going back to that whole tokenization issue, it's not clear how vocabulary size tokenization options will relate to runtime for things like beam search. Note also that if you increase K and M to be arbitrarily large, then you're basically doing brute force exhaustive search, which is, maybe interesting intellectually, but you're probably never going to do that. There's generally no guarantee with beam search, so it doesn't have any kind of nice approximations. There is one interesting paper that argues that there's some sort of cognitive plausibility to beam search, that what it's actually optimizing, given its greediness, actually has something to do with the amount of information that's conveyed by each word. It's a really interesting theoretical paper. It's called "If Beam Search is the Answer, What is the Question?" Something like that. You can find many variations. You can find people adding randomness. You can find people adding pruning. We had a paper where we added something called patience. Lots of variations on this, but I think insofar as you're willing to work with models where you have access to more of the internals, I think there's more that can be done on decoding. There's also a lot of work now on constrained decoding. So if you are working in a setting where you really need your output to be constrained to follow some rules, to meet some spec, to be well-formed grammatical code, I don't know, something like that, there are ways to impose structure on beam search and make it so that it will generate well-formed output. Okay, I want to say a few words about data before we wrap up. In a lecture like this, there's so many things to tell you about evaluation, about the internals of the model, about the connections to statistics, about the architectures. And I think it's very easy I try to remind you at a few points through the lecture, data is really what has made all of this possible. There was a paper back in '93 that basically, even at this point, even before we had the web, people were saying more data is better data. And what we've had since then, of course, is the growth of easy availability of many kinds of data. And now we're working with data sets that are many terabytes or many trillions of words. And they're too big to look at easily. They're too big to talk about in great detail. And often many organizations that are building language models and other AI systems are treating their data as trade secrets. And so one of the things we've been working on is trying to reveal more about how these data sets are built and what the challenges are. So we published last year the DOLMA data set, which is a fully open language modeling data set, and we built models on those data sets. We have new versions of both coming out later this year. I think this is a really, really critically important area because, the data, what is in that data? We don't know. It's too big to know. And yet that is what affects what the models learn. And so there are totally new questions that were not even being asked 10 years ago about the quality of the data, whether the data fairly represents people, how privacy is handled. One of the things we do in our data is we try and remove anything that looks like it could be personal information, like phone numbers. There are also cultural biases in text data. Text emerges as a byproduct of human societies, which have cultural biases, and those are going to show up in the data. There's no way around that. And so then they're going to be repeated. So there's been, I'm sure people in this room are well aware, there's been an extensive study of that and how to mitigate it, how to understand it, what leads to it, and so on. Maybe we can improve the data so that this happens less. Unclear. So, okay. So I just like to say, I think data and evaluation are kind of the two things people talk about less than they should. But there are many exciting problems inside the development of language models beyond the architecture. So we're probably stuck with the transformer for a while. Have fun learning about it tomorrow. It's a great advance. It's really cool. It's also one of the biggest exports from natural language processing to other fields of AI. People are using transformers for like everything now. So I'm quite happy to see us having some influence. For many years, it's always seemed to flow the other direction. But I think if you take in mind this picture, increasing the model capacity, yes. Things that replace the transformer, yes, maybe. Bigger transformers, yes, maybe. But the data, the quality of the data and the amount of data and the selection of the data and the few levers you have for putting inductive bias into your system, I think these are important tools to understand and know about, and maybe where the next breakthroughs are going to be. So everything else here is references. I shared the slides, so they will be available to you. There's probably also a video. We have a good 10 minutes for questions. So fire away.
Thank you for the great talk. Regarding data, I totally agree that ensuring that the data is scrubbed appropriately and it's the highest quality possible for your intended purpose. Is there a paper or something that your team has developed on how to actually the steps to take?
Yeah.
To
Yeah. So the DOLMA paper, Soldani Soldani and et al. 2024, which is ACL last year, talks a lot about this, and basically shares a toolkit for everything we did. What we would like is, we're doing, so I'll say a little bit about the effort. The larger effort is called OLMO, Open Language Model. We started 2.5 years ago, and the idea was NLP and AI more generally used to do really, really well because everybody shared everything about what they were doing. As much as they could, they shared the data. There were always some proprietary data sets. There were always some code bases, but generally people talked very openly about what they were doing. And at the end of 2022, this amazing new artifact came on the scene called ChatGPT, and the tech report was basically a nothing. Like there was just so little information. They said nothing about the data they trained on. And it was like, well, this is not the way we like to play. And so our team was very frustrated and basically came together and said, let's build language models. Let's build some close approximation to these state-of-the-art frontier language models, but do it completely open, meaning we share everything we did. We write a tech report that details everything. We publish the data. We publish all the recipes for the post-training, everything. And so the result of that was sort of 2 streams of work, one on post-training, starting from existing open weight models, because you can do post-training research a lot faster. So we call that series of models Tulu. There's a long story behind the name I won't get into, but basically looking at what are the processes and data recipes for post-training. And then we also started training completely from scratch, and that was OLMO. And we've now had 2 OLMOs. And DOLMA was the data set that we used for the first OLMO. After we published that work, there were a number of efforts where people did extensive semi-automated explorations of building good data sets for pre-training. And those works resulted in new mixes of data and new releases and new sources. And we've continued to pull from that and feed back into it. So there will be a new DOLMA later this year that goes along with the new OLMO coming out later this year. But yeah, I think there's a tremendous amount of work to be done by taking the checkpoints of these training runs for which you know exactly what data was observed since the last checkpoint, and understanding how learning happens and what changes when you're exposed to specific data, and maybe even intervening and rerunning bits of the training. I think this is an incredibly exciting resource, and I'm hoping to see a lot of work building on that. Yeah.
For the horizontal, just simply by increasing the amount of data, and there are a lot of, because you talked about the lack of data in the field, so there are really big companies, some of the papers that I read from these companies that, let's say, double the data or triple the size of data and gets the increase in accuracy of 3%. Actually, it's an insane footprint, or requires insane computational power. So what is your stance on this? Is there like a rule of thumb where you can choose what footprint is worth the increase in accuracy, or is it worth increasing the amount of data in exchange for this much?
Yeah, so I would add a little nuance to that. I mean, generally you add more data, or you make multiple passes over the data, and loss keeps going down and performance generally keeps going up. And yes, it's a diminishing returns thing. The scaling laws stuff that Kyung-Hin showed yesterday, I hate this term scaling laws, by the way. I completely agree. Like, they're not laws, they're empirical observations. But what they're finding is at some point, it's better to not keep training. It would have been better if you had trained a bigger model and looked at less data. And in terms of computation. And so in some sense, you could cast all of that work as trying to find the most efficient way to balance the size of the model against the data. I think there's a lot to be desired in that literature, but that's kind of spiritually, I think that's what they're aiming for. But yes, the point is well taken. There's a huge footprint to these. And, in order to understand these things, you have to train them longer than you would like. And the question is it worth it footprint wise? I mean, this is a values question. I wish I wrote a paper about 5 years ago called Green AI. I wish that we could do all of these things with a lower footprint. I think where I stand right now is there are many things that are contributing to the climate crisis. There are many things that have an energy footprint. This is one of them. We should take it seriously. I encourage work on efficiency, both runtime efficiency and training efficiency. As a bare starting point, documenting the costs and understanding what went into training the models so that we can pay attention to it and put more resources into reducing that. I personally don't think we need, trillion parameter models to do really useful things, especially if we start thinking about specialization. I think we can lower the costs quite a bit, and I want to see more work on that. And I'm happy to see work that, for a long time, I advocated for having specific efficiency tracks at the conferences. They come and they go, conferences are not, they're always changing. But I think this is an incredibly important topic, and it's another thing that I think, if you're, a lot of people here might be in academia and thinking, what can I do when I'm competing against these companies that have massive GPUs? I think the efficiency thing is a realm where there are interesting things to be done in academia, and getting proof of concepts of ideas that will help us do more with less. Someone talked about, using less data to train. I think that's an intriguing idea. How do you filter down and use less data? And get higher quality results. I don't know where the microphones are. Oh, you have one. Go ahead.
Yeah, it works. So I mean, this is like sort of like a longer question. So like I wrote it here. So like, so we started saying, and like, I mean, there's like sort of like the framework that we're working. We try to predict the next word, right? Like that's our task, sort of. But I don't know, like I think that maybe that sort of like misses like the bigger picture in a way, because like so like I was thinking, like, so right now I'm like asking something, but I don't just literally think about like the next word I'm going to say. I have like something else in my mind. I'm trying to get to a point, and that's what actually guides what I say. Like, yeah, but I mean, you get the point, right? So like the thing is, so I feel that many of the things that we saw today are sort of things that try to approximate the idea of I'm gonna try to like have a concept in mind and try to write the words that express this thing, which is not the immediate word all the time. It's more something like more in the distant future, right? And so planning.
The old AI term for this is planning. Sorry, the mic cut off. Yeah.
Yeah. So like you plan for things, right? And so like you have like your recurrent networks where you have like things that went backwards, but of course you can not do that when you're doing like decoding, etc., etc. I don't know, beam search as opposed to greedy search. It's sort of maybe like a sort of planning, etc. So like my question is, why don't we try to like tackle that directly? Like, why don't we work on that specifically? Like, what's the like? I know it's hard, right? But like, why not go for that?
So I think people have, and I think the reason you do see some work like this. I think you can find it if you look in the right places. I can't think of references off the top of my head, but definitely people trying to come up with some kind of structured planning or train the model to get ahead of its words. I think the reason you don't is that there's a general aversion to trying to engineer representations. Like generally the vibe right now, and for some years, has been the model will do a better job of learning how to represent the things it needs to do the task, and you should just focus on what the task is. And I think, if we had really good data showing planning as an output rather than as like this intermediate abstract thing we haven't quite figured out what it looks like, then we could probably focus on it more easily. But I don't think people are going to easily agree on like, what is that concept thing in the middle between what I want to say, where I'm planning what I want to say, and what it's going to be. In fact, the closest thing we have right now is probably something like chain of thought, like let's think step by step, and then it says it in English, and then it says it again. And I find this like super annoying, because like, why should I pay more money for more tokens to get just as bad an answer? But I think there is some belief. Your intuition is shared by a lot of people. I think we're in a rut where everything is next word prediction, and why would we change that when it seems to work so well? Maybe if we just train it on the right data, it'll be good at this. That's a possibility. But I also think there's a general reluctance to get outside the box of like letting the model learn all the representations it needs. We used to have a whole lot more engineered representations in the middle of NLP. The first iterations of this summer school taught parsing, right? Intermediate tree structures for sentences and semantic representations and things like that. We don't do this stuff now, mostly. So a few people do. It still exists in a few places, but by and large, this is not mainstream because we trust that the model is so good at figuring out the intermediate representations. I'm not putting a judgment on this, by the way. I think, we could be very wrong about that. Right now, for the things we're evaluating, they do seem pretty good, but I think there's a lot of things we aren't evaluating yet. So I share the intuition, I agree, but I also kind of understand where the field is at the moment, and people tend to like certain kinds of solutions to things. Right now, end-to-end learning is just, if you can do that, why would you do anything else, is kind of the mentality. One more, okay.
Thank you for the talk. My question is on fairness, actually, because what you said took my interest. So I did a fairness analysis on the model architecture and how we can make fair LLMs, and they were not making sense, as you said, like because everyone focused on architecture, but real world is not fair, and we need more fair data. But then if we have a fair data and then we train our model with this, but the world is unfair, then like what's the trade of this? Because like even our surnames defines our race, our age, where we come from, and they all have a proxies that tends to be sexist, racist, whatever in a model. So like, what do you mean by we can filter data, or we should focus on data more?
So I believe there are many things we can do on the data side, filtering data, deduplicating data, et cetera, that will reduce some of these problems in general. But I don't think that's the end of the story. Right? Personally, I think a big thing we should be focusing on is end use cases and developing interfaces that enable people to do things they want to do, and don't try to do other stuff. Like a doctor trying to do medical diagnosis, take one of the examples from doesn't need a chat. They don't need to have a chit chat with the model about other stuff. Right? A lot of the time, I think the interface doesn't need to be a conversation. It doesn't need to look like a human-human interaction. And I think if you cut away a lot of that, say in specific application, we want to solve this problem, we want to help a person do this kind of work. You don't need a lot of the opportunities for bias to be injected will disappear because you're not having a conversation with it. It's not engaging with you like a human.
Yeah, but then the chatbots will be right, like I don't know, chatbots will have issues because if we don't generalize, yeah, true, but
I would like to get people to be more excited about things that are not chatbots.
yeah, I hate chatbots. Like I'm not a fan of it. Yeah, thank you.
Thank you very much again. Do you think it worth it to continue working on autoregressive models, or do you think there's a big potential to work with diffusion language models or energy-based models? Do they have potential for innovations?
I have not yet seen a compelling
We still have a question here.
It's not exactly a question, but it's more like a comment, agreeing with what you said. I was working on an application. They kind of wanted a chatbot to use for doctors to help them. It was not doctors; it was pharmaceutical people. Basically, they didn't even want like a chatbot, but for some reason there was this pressure to make a chatbot the interface. I don't know why, because obviously for medical applications, you don't want to have hallucinations, so having a chatbot can create like hallucinations and all of those kinds of stuff. And I don't know, maybe we should separate the kind of research that is going to be towards AGI and maybe towards like specific tasks and stuff. I don't know, maybe I think people are very excited about AGI, so they want to put everything under the same umbrella. I don't know, I just have this impression, basically.
Yeah. Sorry. With regard with just said about everything and especially during the lesson that everything is numerical. When we deal with neural networks, we do basically sums, matrix products, and then optimization, which is basically gradient descent. I just want to ask if you really believe that this mathematical paradigm is the right one, or if somehow we should try to find for a paradigm which is different from training everything with using brute force of deep learning, considering that nowadays these models are extremely expensive. So if you think personally that there is a need to come up with new mathematical ideas, and I mean your opinion about this. Thank you.
So I think one of the great things about the field of AI is that we've become empirical. So if somebody has a crazy new idea and they can evaluate it on the same terms as everybody else, then great. So I think I think it's going to be hard to change a lot of people's minds about something that's radically different than the current approach, but it has happened before. If you look at the way AI looked 25 years ago, it was dramatically different. So change can happen, but you have to make good empirical arguments. You appealing to philosophy, appealing to intuitions, it doesn't work. Appealing to mathematical elegance, it doesn't work. So I think that's correct. I think we have to have empirical tests and decide on that basis. We can argue about whether the tests are good, and we should be improving the benchmarks all the time. But I think we have to have kind of a fair way of evaluating that we all agree is reasonable, or as close to reasonable as we're going to get for now. And that is where the arguments should be. A huge amount of time in the history of AI was wasted on kind of feelings people had about one way of doing things versus another. I don't think it works. I don't think that helps move us forward. But that said, I think, best of luck if you've got new ideas about how to do things. Things do change, and new ideas should be welcome. And new ideas about what we should be building and how we should evaluate it should also be welcome.
We still have one question here, and I'm not sure if there's still time or
maybe one more.
All right.
Okay, thank you. I had a question about your projects, Olmo and Tulu, and thank you so much for pushing for them. They're great. So people are now scaling in a new direction, like the time compute direction and via reinforcement learning. So I was wondering if you are going to study that and also develop that inside of Olmo or Tulu, and if so, how are you doing that? Are you mixing reinforcement learning environments that people have pushed? Are you building yourself?
Yeah. So there's definitely the next Olmo and Tulu will have the post-training phase will have a lot more reinforcement learning. We're building a reasoning model. So yes, we had actually Tulu 3 had introduced the term reinforcement learning with verifiable rewards. So the team's definitely been working on that, and there will be definitely more exciting results in that direction. Also in my academic lab, I have a student really doing nice work on, actually a student I met here, doing great work on test time compute and and trying to bring the reward function in at decoding time. I think there's a lot of interesting things that can be done there. So yeah, stay tuned. There's more coming.
Next, speaker.
Thanks.